KitKat, Hershey's, and Cadbury all hide their biggest secret in how the chocolate is formed. These brands have a formula they use for every bar, with nobody being aware of how they are truly made. In this video, we uncover how these brands make their famous products step by step, unveiling the secret methods they use that keep them at the very top of the chocolate industry year after year. KitKat takes its recognizable shape when a towering stack of paper-thin wafers and chocolate-based filling reaches a cutting machine that slices the enormous layered sheet into long, perfectly parallel fingers. A moment earlier, the product looks more like a giant rectangular wafer board than a chocolate bar. Then synchronized blades descend through the crisp layers, dividing the sheet with extraordinary precision, while tiny crumbs scatter onto the conveyor below. The individual fingers are recognizable, but they are still pale, exposed, and completely missing the smooth chocolate shell that will eventually surround them. Before that coating can be applied, the fragile wafer structure must survive cutting, alignment, cooling, and transport without losing the delicate internal layers responsible for the characteristic KitKat snap. The wafer itself starts much earlier as a fluid batter. Flour is delivered from enclosed storage into automated weighing equipment, while water and the remaining wafer ingredients are metered separately. Large industrial mixers combine them under controlled agitation, producing a batter much thinner than bread or cake dough. That fluid consistency is deliberate because the mixture must spread into an extremely thin layer across the baking plates. Mixing continues until dry pockets disappear and the batter flows with consistent viscosity. If it becomes too thick, the wafer sheet can emerge heavy or uneven. If it becomes too thin, the finished sheet may lack enough structure to survive the stacking equipment farther down the line. From the mixing system, pumps send the batter toward a continuous bank of wafer ovens. These machines operate very differently from ordinary tunnel ovens. Instead of placing a tray inside a heated chamber, the production line uses large pairs of patterned metal baking plates that repeatedly open, receive a measured dose of batter, close under pressure, travel through the heated section, and open again. Each portion spreads rapidly between the plates until it forms a wafer sheet only a few millimeters thick. Heat reaches the batter from both sides simultaneously, driving moisture outward at remarkable speed, while the plate pattern presses the familiar fine texture into the surfaces. When the plates reopen, an entire wafer sheet appears almost instantly, light, rigid, and extremely brittle. Mechanical extraction systems lift it away and transfer it onto cooling conveyors before the next dose enters the same baking position. Across the oven, this cycle repeats continuously. Plates open and close in sequence, like a giant mechanical book, creating sheet after sheet at a rate impossible to achieve with individual baking trays. But the freshly baked wafers cannot be stacked immediately. They are hot, dry, and vulnerable to warping, so their next stage is less dramatic but just as important. The sheets move through a controlled cooling and conditioning section where air circulates across both surfaces. As their temperature falls, the wafer structure stabilizes and moisture becomes more evenly distributed. Conveyor guides keep the thin sheets separated enough to prevent trapped heat from accumulating between them. The cooling profile must remain controlled because the wafer's crispness depends heavily on moisture. Too much retained water softens the structure, while excessive drying can make it so brittle that the later cutting equipment creates uncontrolled fractures instead of clean fingers. While hundreds of wafer sheets are cooling, another production stream is preparing the material that will bind them together. KitKat's internal layers are not assembled by simply pouring ordinary melted chocolate between bare wafers. A specially prepared filling is mixed to produce the correct consistency for spreading in a very thin, uniform layer. Chocolate-derived ingredients, fats, sugar-containing components, and finely processed material are blended and refined until the filling can move through pumps while still having enough body to remain between the wafer sheets rather than squeezing out uncontrollably. One particularly efficient part of confectionery production can occur here. Wafer fragments and clean product material generated during trimming or cutting can be finely processed and incorporated into an appropriate filling stream under controlled manufacturing conditions rather than simply remaining as loose pieces. Milling equipment reduces suitable material into much smaller particles before it is blended into the filling. By the time the mixture reaches the spreading system, those particles have become integrated into a smooth, consistent mass capable of being deposited across entire wafer sheets. Now the crisp wafer and soft filling finally meet. A wafer sheet enters the layering machine and passes beneath a spreading head that applies a precisely controlled film of filling across nearly the entire upper surface. Another wafer sheet is positioned directly on top. Filling is applied again, followed by another wafer. The sequence repeats until the programmed number of crisp layers has been assembled. The machine builds not individual bars, but enormous multi-layer wafer sandwiches, each one containing the same repeating pattern. Wafer, filling, then wafer again. The thickness of every filling layer matters because small variations multiply when several layers are stacked. Metering pumps therefore maintain a controlled flow while spreading equipment distributes the filling across the sheet from edge to edge. Mechanical guides align each new wafer before contact, preventing the stack from drifting sideways as its height increases. The completed sandwich may be many times larger than a finished KitKat bar, but internally it already contains the architecture that will eventually be visible when a finger is broken in half. Freshly assembled wafer books are still too soft for aggressive cutting. The filling between the layers needs to firm enough to lock the structure together, so the large sheets enter a cooling tunnel. Conditioned air removes heat while the filling becomes increasingly stable. The wafers themselves remain crisp, but the internal layers now act like an adhesive matrix, holding the sandwich together as one machinable slab. This is the moment that makes the next transformation possible, because the factory is about to turn a single giant sheet into hundreds of precisely sized centers. The cooled slabs reach the cutting line and are first squared or trimmed where necessary. Longitudinal blades divide them into narrow strips, while cross-cutting systems establish the final length. The cutting geometry depends on the KitKat format being produced, but the objective is always repeatability. Every center must fit downstream chocolate coating equipment and ultimately the wrapper surrounding it. Servo-controlled conveyors maintain exact spacing between cuts, while extraction systems remove loose crumbs before they can interfere with the chocolate stage. The freshly cut centers spread into organized lanes. At this point, their cross-sections expose the repeating wafer and filling layers clearly, but the outer surfaces remain almost entirely uncovered. Even the edges created by cutting are exposed. That is about to change dramatically. In another section of the factory, chocolate has been undergoing its own preparation process, and the way that chocolate is cooled before coating determines whether the finished KitKat develops the smooth surface and clean break expected from the final shell. Chocolate arrives in bulk or is prepared in large heated vessels where controlled warming converts it into a uniform liquid. Agitators keep the mixture circulating while preventing temperature differences from developing across the tank. The liquid then passes into tempering equipment, where it undergoes a carefully managed heating and cooling sequence. Chocolate contains cocoa butter capable of crystallizing into different structures, but the coating needs a stable crystal form that produces the desired gloss, firmness, and snap. Tempering encourages those stable crystals before the chocolate ever touches a wafer. The tempered chocolate is pumped continuously toward the enrobing line. KitKat centers arrive in evenly spaced rows on an open mesh conveyor and move directly beneath a broad curtain of flowing chocolate. The instant each center passes through, the top and sides disappear beneath the coating. At the same time, chocolate reaches the underside through a controlled bottoming system so the exposed wafer becomes completely enclosed. In only seconds, a pale layered center turns into a glossy chocolate-covered bar. Hershey's chocolate first becomes a recognizable bar when warm, perfectly tempered chocolate surges from a row of depositing nozzles and fills polished molds, moving continuously beneath them. Each cavity receives a precisely measured dose. Then, the entire mold begins vibrating hard enough to make the glossy chocolate ripple from edge to edge. Those vibrations flatten the surface and drive trapped air upward before the chocolate enters a cooling system that will turn the flowing mass solid. But the most important transformations have already happened. Hours earlier, the same chocolate existed as cocoa beans, sugar, milk ingredients, and cocoa butter, following separate production paths. Before those ingredients can fill a single mold, the factory must break cocoa beans apart, refine their particles to microscopic dimensions, develop the chocolate's texture, and control how its cocoa butter crystallizes. Cocoa beans begin by passing through cleaning and sorting equipment. Screens separate material by size, while aspiration systems use moving air to remove lighter unwanted particles. Magnets and additional separators capture foreign material before the beans continue. The cleaned cocoa then enters roasting equipment, where carefully controlled heat develops the characteristic roasted cocoa profile while reducing remaining moisture. Large rotating roasters or continuous roasting systems keep the material moving so heat reaches it evenly. Temperature and residence time are tightly regulated because the beans are not simply being dried. Their internal flavor chemistry is changing as the roast progresses. After roasting, the beans cool before entering cracking equipment. Rollers break the brittle shells and kernels into smaller fragments, producing a mixture of shell pieces and dense cocoa nibs. The next machine separates them using differences in weight. Air currents lift away the lighter shell fragments, while the heavier nibs fall into dedicated collection streams. What remains no longer resembles a cocoa bean. These dark fragments contain the cocoa solids and cocoa butter that will form the foundation of the chocolate, and the next machine releases that fat without adding a drop of liquid. Cocoa nibs enter industrial grinding mills, where intense mechanical pressure reduces them into progressively smaller particles. Friction generates heat, melting the cocoa butter naturally contained inside the nibs. A dry pile of fragments gradually becomes a thick, flowing material known as chocolate liquor or cocoa mass. Despite the name, it contains no alcohol. It is essentially finely ground cocoa, suspended in its own melted fat. Pumps can now move it through heated pipes toward the mixing area, where the dark cocoa stream will finally meet the ingredients responsible for sweetness and milk character. For Hershey's milk chocolate, milk ingredients follow their own preparation route before joining the cocoa. Hershey's manufacturing is known for a distinctive milk processing approach that contributes to the characteristic flavor of its milk chocolate. Milk components are concentrated under controlled conditions, reducing water while preparing them for incorporation into the confectionery system. Sugar is measured separately through automated dosing equipment. Cocoa mass, milk-derived ingredients, sugar, cocoa butter, and other formulation components are then combined in large mixers, transforming several dramatically different materials into a dense chocolate paste. At this stage, the mixture would not yet feel like a finished Hershey's bar. Sugar and cocoa particles remain far too large, creating a gritty sensation. The chocolate, therefore, enters refining equipment, commonly using a series of heavy rollers positioned with progressively smaller gaps. The paste is drawn between these rollers repeatedly, crushing solid particles until they become extremely fine. Instead of leaving the refiner as a glossy liquid, the material can emerge as thin flakes or a dry-looking powdery mass because the enormous increase in particle surface area changes how the available fat coats the solids. Those refined particles now enter conching equipment, and this is where texture begins changing dramatically. Large mixers knead, shear, turn, and aerate the chocolate for an extended period while temperature remains. Carefully controlled, the constant mechanical movement redistributes cocoa butter across the microscopic particles, reduces remaining moisture, and allows volatile compounds to escape. Additional cocoa butter and emulsifying ingredients can be introduced according to the formulation, gradually changing the thick refined mass into a smoother, more fluid chocolate. The conche may look like an oversized industrial mixer, but the physical changes inside it are crucial. Chocolate repeatedly folds over itself as heavy mixing elements drag through the mass. Friction and controlled heat keep the cocoa butter fluid. Over time, rough particle surfaces become increasingly coated with fat, reducing internal resistance and improving flow. The chocolate leaving this stage finally has the smooth mouth feel associated with a finished bar, yet pouring it directly into molds would still create problems. The cocoa butter crystals have not been organized correctly. Tempering handles that microscopic challenge. The finished chocolate flows through a sequence of carefully controlled temperature zones. First, heat ensures unwanted crystal structures are melted. The chocolate is then cooled so stable cocoa butter crystals begin forming, followed by gentle reheating that removes less desirable crystals while preserving enough of the stable form to guide solidification later. Nothing obvious changes visually. The chocolate remains dark and fluid throughout. Internally, however, its fat structure has been prepared to produce a firm bar with a smooth surface and clean break. Now the tempered chocolate reaches the depositing line from the opening scene. Empty molds travel beneath multiple nozzles in perfect synchronization. Pumps deliver measured quantities into each cavity, and the mold immediately enters a vibrating section. Rapid vibration spreads chocolate into corners, levels the upper surface, and encourages trapped air bubbles to rise. The molded details are reproduced directly from the cavity, so lettering, borders, and break lines can all appear as the liquid presses against the shaped surface. Filled molds then disappear into long cooling tunnels. Cold air does not simply freeze the chocolate as quickly as possible. Cooling is carefully staged so the stable cocoa butter crystals encouraged during tempering can develop throughout the bar. As heat leaves, the glossy liquid becomes increasingly rigid and contracts slightly away from the mold surface. That small contraction becomes useful later because it helps the solid chocolate release cleanly. When the molds emerge, automated demolding equipment turns or flexes them in a controlled motion. The finished Hershey's bars separate and settle onto conveyors with their molded surfaces fully visible. What entered the cooling tunnel as flowing chocolate now moves as thousands of rigid bars arranged in precise lanes. Conveyor guides maintain spacing while cameras inspect shape, surface appearance, and major molding defects. Broken or irregular pieces are diverted before packaging. The accepted bars now approach wrapping machinery operating at much higher speed than the earlier chocolate-making equipment. Printed packaging material unwinds from enormous reels through tension rollers. Registration sensors detect marks on the film and synchronize each printed section with an approaching bar. The material folds around the chocolate as forming guides bring its edges together. Sealing equipment closes the package, and cross-cutting mechanisms separate one wrapped bar from the next without stopping the continuous flow. Different Hershey's products can use different wrapper structures and package formats, but the machinery follows the same fundamental requirement: isolate each finished bar while maintaining precise alignment at high speed. Production codes are applied as packages continue along the conveyor, and inspection cameras verify print position, seals, and coding. Dynamic check systems can remove packages outside program specifications without interrupting the stream behind them. Wrapped bars then accumulate before secondary packaging. For multi-packs, automated counting systems divide the stream into predetermined groups. Paperboard blanks are pulled from magazines and mechanically opened or folded around those groups. For larger shipping configurations, corrugated cases are erected from flat blanks, while loading equipment places the required quantity of finished packages inside. Flaps fold inward, hot melt adhesive is applied, and compression belts hold each carton closed until the bond stabilizes. The final machines handle entire cases rather than individual chocolate bars. Conveyors rotate cartons into predetermined orientations and assemble complete pallet layers. Automated palletizers transfer each layer onto a waiting pallet, building the load upward according to a pattern designed to keep the cases stable. Once the programmed height is reached, stretch film begins circling the stack from the base. The wrapping carriage rises while maintaining controlled tension, binding the cartons together into one transport unit. Cadbury chocolate slides out of its molds only after the entire tray is turned upside down and given a precisely controlled mechanical flex, releasing row after row of solid bars onto a moving conveyor. The molded squares, grooves, and lettering are already sharply defined, and the surface carries the smooth finish created as the chocolate hardened against polished metal or polymer cavities. Yet only a short time earlier, that same chocolate was a warm liquid flowing through heated pipes. Go farther back, and it was an abrasive mixture of cocoa, sugar, and concentrated milk ingredients. The real manufacturing challenge is therefore not simply melting ingredients together. Cadbury's production line has to transform cocoa beans and milk into particles so fine they disappear on the tongue, then manipulate cocoa butter crystals with extraordinary temperature precision before a bar can ever leave its mold. The cocoa route starts with beans being cleaned before any chocolate processing begins. Vibrating screens separate material according to size. Aspiration equipment removes lightweight fragments with controlled airflow, and magnetic separators capture metallic contamination from the moving stream. The cleaned cocoa is then exposed to carefully regulated roasting conditions. Depending on the plant and process configuration, roasting can occur at different stages of cocoa preparation, but the objective is controlled flavor development and moisture reduction. Heated air moves around the cocoa, while temperature and residence time are regulated continuously. The beans darken, their aroma intensifies, and their shells become increasingly brittle. That brittleness is useful because the next machines have to remove the shell without throwing away the valuable center. The roasted material passes into cracking equipment, where rollers break the beans into irregular fragments. Inside each bean are pieces of cocoa kernel called nibs, mixed now with fragments of the brittle outer shell. Winnowing equipment separates the two using their different densities. Air currents lift lighter shell pieces away, while heavier cocoa nibs continue downward. The resulting nib stream looks dry and granular, but roughly half of its mass can consist of cocoa butter. Once powerful grinding equipment begins crushing those cellular structures, that hidden fat completely changes the material. Mills reduce the nibs through repeated grinding and shearing. Friction raises their temperature, cocoa butter melts, and the fragments gradually stop behaving like dry solids. They become a dark, viscous fluid called cocoa liquor or cocoa mass. Nothing has been added to make it liquid. The cocoa's own fat provides the flowing phase. Pumps move this warm cocoa through jacketed pipes towards storage and mixing systems, while part of the cocoa stream can also be processed into cocoa butter and cocoa solids, depending on the recipe requirements. But Cadbury milk chocolate needs another major component, and its preparation follows a very different route. Milk and sugar are brought together through the characteristic milk chocolate processing sequence associated with Cadbury. Fresh milk is concentrated by removing much of its water under controlled heating and evaporation. Sugar is incorporated as the milk becomes increasingly concentrated, producing a thick milk and sugar mixture. Cocoa components can then be combined with this concentrated material, which is further processed until much more moisture has been removed. Rather than remaining as a wet dairy mixture, it becomes a concentrated intermediate, often associated with Cadbury's distinctive milk chocolate manufacturing approach. Drying changes that mixture dramatically. Water is one of chocolate manufacturing's biggest complications because even relatively small amounts can interfere with how sugar, cocoa solids, and fat behave together. The concentrated milk mixture is therefore processed until it becomes suitable for incorporation into the low moisture chocolate system. What started as fluid milk has now become a dense source of milk solids, sugar, and developed flavor components. And this is where the separate cocoa and dairy routes finally converge. Measured cocoa mass, prepared milk ingredients, sugar, cocoa butter, and the remaining recipe components enter industrial mixing equipment. Heavy paddles fold the ingredients repeatedly while the fat begins coating enormous numbers of solid particles. The mixture initially resembles a dense paste rather than the silky liquid associated with melted chocolate. If this material were allowed to solidify now, its texture would be noticeably coarse because individual sugar and cocoa particles are still too large. The next machine attacks that problem mechanically. Chocolate refining equipment forces the mixture through a series of rollers separated by extremely narrow gaps. Each successive gap becomes smaller, crushing the particles progressively rather than attempting the full reduction in one step. The chocolate spreads into thin films under tremendous pressure as it moves between the rollers. Sugar crystals fracture, cocoa and milk solids become finer. By the final roller, the particles have been reduced to dimensions small enough that the finished chocolate can feel smooth rather than gritty. Curiously, the refined material may look less like chocolate than it did before. Increasing the total surface area of millions of particles means the available fat has far more material to coat, so the output can emerge as delicate flakes or a dry-looking powdery mass. It has the correct particle size, but not yet the correct flow. That transformation happens in the next stage, where heat and mechanical movement rebuild the refined material into smooth chocolate. The flakes enter conchis, or intensive chocolate mixers. Large mixing elements sweep through the mass continuously, folding, compressing, and shearing it, while carefully controlled heat keeps cocoa butter mobile. Additional cocoa butter and emulsifying ingredients can be introduced according to the formulation. Gradually, the fat spreads across the newly refined particle surfaces. Internal friction falls, and the mixture changes from a heavy, almost crumbly material into a glossy fluid capable of flowing through pipes and depositing nozzles. Conching also changes the chocolate beyond simple fluidity. Continued movement helps distribute flavor compounds throughout the mass, drives off traces of unwanted moisture, and allows volatile components to escape. The chocolate repeatedly stretches and folds as powerful mixers work through enormous batches. Temperature, mixing intensity, and time are adjusted to produce the required viscosity and flavor profile. By the end, the material finally looks like the chocolate that will become a Cadbury bar. But its internal cocoa butter structure is still uncontrolled, and the next stage is almost invisible despite being one of the most important. tempering sends the liquid chocolate through a programmed temperature curve. The chocolate is heated, so existing cocoa butter crystal structures are removed, cooled under controlled agitation to encourage crystallization, and then brought to a carefully selected working temperature. Cocoa butter can solidify in several crystalline arrangements, but only certain stable forms produce the desirable combination of gloss, firmness, contraction, and clean snap. The tempering machine therefore manipulates crystals measured on a microscopic scale, while thousands of kilograms of chocolate continue moving through the production system. Only now can molding begin. Empty bar molds travel in an uninterrupted procession beneath depositing heads. Multiple nozzles open simultaneously, releasing exact portions of tempered Cadbury chocolate into the cavities below. Pumps meter the quantity, so every bar reaches the required dimensions and mass. The molds immediately enter vibration tables, where rapid mechanical movement makes the liquid surface tremble. Chocolate spreads into corners, and embossed details, while trapped air bubbles rise away from the molded face. The molds then enter a long cooling system, but simply making them as cold as possible would undermine the careful work performed during tempering. Instead, cooling proceeds under controlled conditions that allow the desired cocoa butter crystal network to develop throughout the bar. Heat moves from the chocolate through the mold and into circulating conditioned air. The surface solidifies first, followed progressively by the interior. As crystallization advances, the chocolate contracts slightly, pulling away from the cavity walls. That tiny contraction sets up the opening scene. At the demolding station, trays rotate or flex mechanically. Solid bars release from their cavities and settle onto conveyors, while empty molds loop back toward the depositor to begin another cycle. The bars now have their final geometry, but the line immediately separates and spaces them for inspection. Cameras examine surfaces and edges, while sensors identify major dimensional or molding defects. Any bar that has fractured, filled incorrectly, or failed to release cleanly can be diverted before wrapping. Maltesers begin with a brittle malt center expanding into a tiny honeycomb sphere. The center is the part that makes the product different from an ordinary chocolate ball. It is light, crisp, and porous, with a dry snap inside a smooth milk chocolate shell. The manufacturing line is designed to build that contrast in stages. First the malted center, then the rounded shape, then the chocolate layers, then polishing, cooling, weighing, bagging, and final packing. The malt center starts as a cooked mixture. Malt extract, sugar, glucose syrup, milk ingredients, and other dry components are measured into a controlled batching system. The ingredients enter mixing vessels, where heat and agitation turn them into a thick syrup. The syrup must be uniform before it can be aerated and expanded. Malt extract gives the center its toasted, cereal-like flavor. It blends into the sugar system as the liquid warms. The mixture becomes darker, thicker, and more elastic. Agitators keep it moving so the sugars do not settle or burn against heated surfaces. The syrup then moves into a cooking stage. Heat drives off moisture and concentrates the sugars. The liquid becomes more viscous as water evaporates. Its temperature and solids level must reach the correct point, because the final texture depends on how the sugar structure sets after expansion. At this stage, the mixture is still dense. It has flavor, sweetness, and malt character, but it does not yet contain the light honeycomb structure. That structure forms when the cooked mass is expanded. Gas generation or aeration creates tiny cavities inside the hot sugar malt mixture. The expanding gas pushes through the softened mass, forming a network of bubbles. The bubbles stretch the syrup into thin walls. As the mixture cools, those walls harden into a crisp, porous structure. The material changes quickly. A heavy syrup becomes a lighter foam-like mass. It is not soft like whipped cream. It is a hot sugar structure full of trapped voids. When it sets, it becomes brittle and dry. The expanded malt mass is cooled and broken down into smaller pieces. It may be formed into rough pellets, cut, screened, or milled into controlled fragments before shaping. The goal is to create center pieces that can be rounded into small balls of consistent size. The pieces pass through sizing equipment. Screens remove fines and oversized fragments. Airflow can pull away light dust. The accepted pieces move into rounding equipment. The centers tumble inside rotating pans or drums, where their edges are gradually worn down. Rounding is slow and mechanical. The rough pieces roll against each other and against the drum surface. Corners break away. Flat faces soften. Each piece becomes closer to a sphere. Small additions of binding material or syrup may help the particles build a smoother surface as they tumble. The center does not need to be perfectly polished yet. It only needs the right size, shape, and strength for chocolate coating. If the center is too rough, the chocolate shell becomes uneven. If it is too fragile, it will break during panning. If it is too dense, the final bite loses the light Malteser's texture. The rounded malt centers move through a drying and conditioning stage. Warm air reduces surface moisture and stabilizes the texture. The centers must be dry before chocolate is applied. Moisture would interfere with coating and could make the chocolate grip unevenly. Before coating, the centers are inspected and classified. Small broken pieces are removed. Oversized centers are separated. Dust is screened away. A clean, dry stream of malt balls then moves toward the chocolate panning area. Milk chocolate is prepared in a separate system. Cocoa ingredients, milk powder, sugar, cocoa butter, and vegetable fat or other formula components are mixed and refined. The mixture passes through rollers that grind the particles smaller. Refining gives the chocolate a smoother mouthfeel by reducing the size of sugar and cocoa particles. After refining, the chocolate is conched. In conching machines, heavy mixing arms continuously move the chocolate for a controlled time. The process smooths the texture, distributes fat around the dry particles, and develops the final flavor. The chocolate becomes glossy, fluid, and uniform. The chocolate must then be tempered. Tempering controls how the fat crystals form. The chocolate is cooled and gently reheated through a precise temperature curve. This creates stable crystals that help the coating set with a clean finish. Proper tempering gives the shell firmness and reduces dullness or soft texture. The malt centers enter coating pans. These are large rotating drums, angled so the centers tumble continuously. A measured amount of tempered milk chocolate is sprayed or ladled onto the moving centers. The chocolate touches the dry malt balls and spreads as they roll. The first layer is thin. It seals the porous center and creates a smoother surface for later layers. The centers continue tumbling while cool air passes through the pan. The chocolate sets around each piece. Once the layer is firm enough, another small addition of chocolate is applied. The coating builds gradually. Maltesers are not coated with one heavy pour of chocolate. The shell forms through repeated thin layers. Each layer must spread, set, and bond before the next layer arrives. This creates a rounded, even chocolate covering without flooding the centers or joining them together. The sound inside the pan changes as the shell thickens. At first, the centers make a dry rattling sound. As chocolate builds, the movement becomes softer and heavier. The pieces roll over one another with a smoother, duller sound. The pan speed, air temperature, chocolate temperature, and addition rate all control the shell. If chocolate is added too quickly, pieces stick together. If air is too cold, the coating can set before it spreads. If air is too warm, the surface stays tacky. The machine balances movement, temperature, and timing until each ball reaches the correct size. After the main chocolate coating is built, the pieces continue tumbling to smooth the surface. Small ridges are evened out by rotation. The shell becomes more uniform with every turn. The pieces are now recognizable as Maltesers, but they still need finishing. A polishing stage may apply a very thin finishing layer. The pieces tumble while a glazing or polishing material is added in tiny amounts. This gives the chocolate surface a smooth, lightly glossy appearance and helps reduce scuffing during packaging. The finished pieces then move into cooling. They travel through a cooling tunnel or controlled room where air removes heat from the shell. The chocolate firms fully. The coating becomes stable enough for weighing, conveying, and bagging. After cooling, the Maltesers pass through inspection. Screens remove broken pieces, dust, and double pieces stuck together. Metal detection checks the product stream. Optical systems can detect unusual shapes, exposed centers, dull patches, or oversized clusters. Rejected pieces are separated from the main flow. The accepted pieces move into holding hoppers above the packaging line. The hoppers are designed to keep the chocolate pieces moving gently. Sharp drops are avoided because the coating can scuff or chip. Controlled gates feed the product into weighing systems. Multi-head weighers portion the Maltesers into exact amounts. The pieces fall into small weighing buckets. The control system selects the best combination of buckets to reach the target weight. Gates open and the measured amount drops into the bagging machine. For small bags, packaging film unwinds from a roll. The film passes over a forming collar and wraps into a tube. A vertical heat seal closes the back seam. The weighed Maltesers drop into the open tube. Horizontal sealing jaws close the bottom and top seals, forming individual bags. The sealed bag passes under a coder. Production information is printed onto the film. The bag then moves through check weighing. Any underweight or overweight pack is rejected automatically. For boxed formats, the pieces may be weighed into a bag first, then inserted into a carton. Flat paperboard blanks are opened into box shapes. The filled inner pack slides inside. Folding rails close the flaps. Adhesive or locking tabs hold the carton shut. Twix begins as a long sheet of biscuit dough moving toward a cutting line. The dough is built to become a crisp base. It must be strong enough to carry caramel, but light enough to snap cleanly under the chocolate shell. The process starts with flour, sugar, fat, leavening ingredients, salt, and water entering a controlled mixing system. Dry ingredients are weighed first. Flour flows from storage bins through enclosed conveyors. Sugar and smaller powders are added through separate dosing units. Each ingredient passes into a mixer in measured amounts. The mixer does not simply stir the powders. It builds a dough with the right texture for sheeting, cutting, baking, and coating. Fat is added to create the short, crumbly biscuit texture. It coats part of the flour and limits gluten development. This is what helps the biscuit break cleanly instead of becoming chewy. Water enters slowly, just enough to bind the dry ingredients. The mixer blades fold, press, and turn the mass until it becomes a firm dough. The dough exits the mixer in heavy pieces. It is fed into a hopper above a sheeting machine. Large rollers pull the dough downward and compress it into a thick sheet. The sheet passes through more rollers, each pair reducing the thickness. The surface becomes smoother with every pass. The dough sheet must reach a precise thickness. If it is too thick, the biscuit will bake slowly and make the bar heavy. If it is too thin, it can crack under the caramel layer. The sheeter controls the height with adjustable roll gaps. Once the sheet is even, it moves under cutting rollers. The rollers score and cut the dough into long, narrow biscuit fingers. Small holes may be docked into the surface. Docking lets steam escape during baking and helps prevent the biscuit from puffing unevenly. The shaped dough pieces transfer onto an oven band. The band moves continuously through a long baking tunnel. Heat surrounds the dough from above and below. Moisture begins leaving the biscuit. The surface firms first, then the center dries and sets. Inside the oven, the dough changes from pale and soft to golden and crisp. The fat melts, water evaporates, and the structure becomes rigid. The biscuit pieces shrink slightly as they bake. Their edges sharpen, and the surface develops a light toasted color. The oven has different temperature zones. The first zone sets the shape. The middle zones drive off moisture. The final zones finish the color and texture. The goal is a biscuit that is dry, crisp, and strong enough for high-speed handling. The baked biscuit fingers leave the oven and enter a cooling section. Air flows over and under the pieces. Cooling is important because caramel cannot be applied properly to hot biscuits. If the biscuit is too warm, the caramel may spread too much or soften the structure. The cooled biscuits travel in straight lanes. Conveyor guides align them precisely. The next layer is caramel. Caramel is prepared in a separate cooking system. Sugar, glucose syrup, milk ingredients, fat, and water are mixed in heated vessels. The mixture starts as a pale liquid. As it cooks, water evaporates and the sugars concentrate. The liquid thickens and develops a smooth, stretchy body. The caramel must be cooked to a very specific texture. It cannot be too runny, or it will flow off the biscuit. It cannot be too firm, or it will not deposit evenly. The finished caramel must hold its shape as a layer, but remain soft enough to bite through. After cooking, the caramel is cooled to a controlled depositing temperature. It remains warm and pumpable. Pipes carry it to the depositor above the biscuit lanes. The depositor contains nozzles matched to the spacing of the biscuits. As each biscuit passes underneath, a ribbon of caramel is laid along the top. The caramel lands as a smooth strip, following the length of the biscuit. The depositor times each flow so the caramel starts and stops at the right point. It must not hang over the ends too far, because excess caramel can interfere with chocolate coating. The caramel-topped biscuits continue forward. Cooling air firms the caramel surface. The layer becomes stable enough to move, but it remains soft inside. The product now has the basic Twix structure: biscuit base and caramel top. Some lines form the biscuit and caramel as long continuous strips before cutting. In that version, caramel is deposited onto long biscuit slabs. The slabs then pass through slitting and guillotine cutting systems that divide them into individual bars. The cutting blades must pass cleanly through caramel and biscuit without dragging the layers out of position. The formed bars are spaced apart before chocolate coating. Correct spacing matters because the enrober must cover every side without bars touching each other. Vibrating conveyors and timing belts create even gaps between the pieces. Milk chocolate is prepared in another part of the factory. Cocoa ingredients, sugar, milk powder, cocoa butter, and fats are blended into a chocolate mass. The mixture is refined through rollers that reduce particle size. This gives the chocolate a smooth texture instead of a gritty one. The refined chocolate is conched. Heavy mixing arms move the chocolate for a controlled time. The mass becomes smoother, more fluid, and more uniform. The fat coats the dry particles evenly. The chocolate develops the proper flow for coating. Before it can cover the bars, the chocolate is tempered. Tempering controls the crystal structure of the cocoa butter. The chocolate is cooled and warmed through a precise temperature curve. Stable crystals form, allowing the coating to set with a firm surface and clean snap. The Twix bars enter the enrober on a wire mesh belt. A curtain of tempered milk chocolate falls from above. Each bar passes through the curtain and chocolate flows over the caramel top, down the sides, and around the biscuit edges. At the same time, chocolate is applied from below. The mesh belt allows chocolate to coat the underside. the bar becomes fully covered. Excess chocolate drains through the belt and returns to the tempering system. After the curtain, the bars pass under air blowers. These blowers remove extra chocolate from the top and sides. The airflow smooths the coating and controls shell thickness. Too much chocolate would make the bar heavy and uneven. Too little would expose biscuit or caramel. The coated bars then pass over a vibrating section. The vibration helps remove trapped air bubbles and evens the chocolate surface. The shell becomes smoother as the bar continues forward. The surface pattern forms as the chocolate settles. Twix bars often have a slight ripple or flow texture on top because the chocolate curtain, airflow, and movement shape the coating before it sets. The ridges are not carved after cooling. They form while the chocolate is still fluid. The bars enter a cooling tunnel. Inside, chilled air circulates around them. The chocolate shell begins to crystallize and harden. Cooling must be controlled carefully. If it is too fast, the coating can become dull or crack. If it is too slow, the chocolate may remain soft and mark during wrapping. As the bars move through the tunnel, the shell changes from glossy liquid to firm chocolate. The caramel stays enclosed. The biscuit remains dry because the coating seals it from the outside. At the end of cooling, the bars leave the tunnel fully set. They pass through inspection. Cameras check shape, size, coating coverage, and surface defects. Metal detectors scan the product stream. Bars with exposed biscuit, missing chocolate, broken edges, or distorted caramel are rejected automatically. Accepted bars move toward wrapping. Twix bars are usually packed as paired fingers or single bars depending on the format. Lane systems align the bars and bring them into the required grouping pattern. For a twin pack, 2 bars are placed side by side with controlled spacing. The wrapper begins as a roll of printed film. The film unwinds and passes through rollers that control tension. It moves around a forming box, where it wraps around the bar or bar pair. The product enters the film tube in perfect timing with the print registration. A longitudinal seal closes the film along the back or underside. Heated sealing wheels, or jaws, press the film layers together. Then cross-seal jaws close the ends of each pack. The jaws seal and cut at the same time, separating one wrapped pack from the next. Bounty begins with shredded coconut being turned into a compact, moist center. The coconut is the main structure of the bar. It does not start as a smooth paste. It starts as small white flakes with a fibrous texture. Each flake must be hydrated, sweetened, bound together, shaped into bars, covered with chocolate, cooled, wrapped, and packed without losing the soft coconut bite inside. The coconut arrives in dry, shredded form. It is stored in ingredient bins or bags before feeding into the mixing area. The flakes are light and irregular. Some pieces are longer, some are finer. The production system controls the blend, so the finished center has an even texture. Before mixing, the coconut may pass through screens. Oversized pieces are separated. Very fine dust can be reduced. The goal is not to make the coconut perfectly uniform, but to keep the texture consistent enough for forming. The center must hold together, but it still needs visible coconut fibers. A syrup phase is prepared separately. Sugar, glucose syrup, water, and milk-based ingredients are measured into heated vessels. The liquid warms as agitators turn. The sugar dissolves into the water and syrup base. The mixture becomes glossy and smooth. This syrup is the binder. It gives the coconut center sweetness, moisture, and shape retention. It must be thick enough to hold the flakes together, but not so thick that it forms a hard candy texture. The final bar needs a soft pull when bitten, not a brittle snap. Fat ingredients are added into the warm syrup system. They help create a creamy texture and reduce dryness in the coconut mass. The warm liquid becomes richer and more opaque as the fat disperses. Mixing keeps the binder even so no area becomes greasy or thin. The syrup is cooked to a controlled solids level. Water evaporates as heat continues. The mixture thickens slightly. The factory does not rely on appearance alone. Temperature, time, and flow controls keep the binder within the correct range. The shredded coconut then enters a heavy-duty mixer. The dry flakes drop into the bowl or continuous mixing chamber. The warm binder is added gradually. The mixer turns slowly at first, folding syrup into the coconut. Then the paddles increase their work, pressing and lifting the mass. The texture changes quickly. Dry flakes become damp. Loose coconut turns into a cohesive mixture. The white fibers become glossy as the binder coats them. The mass begins to clump, but the mixer prevents large lumps from forming. This is one of the most important stages in bounty production. If the coconut receives too little binder, the center will crumble. If it receives too much, the bar will feel sticky and heavy. If mixing is too rough, the flakes break down and the texture becomes pasty. The machine must combine the ingredients while preserving the fibrous coconut structure. The finished coconut mass is warm, moist, and thick. It cannot be poured like liquid. It must be pressed, extruded, or sheeted into the correct bar shape. The mass feeds into a forming machine. In one method, it is forced through a wide rectangular die as a continuous slab. Rollers or belts control the height and width. The surface is leveled as the coconut sheet moves forward. The sheet must be dense enough to stay together, but not compressed so hard that the center loses its softness. Another method forms the coconut mass into long ropes. The mixture passes through shaped openings, producing continuous bars with rounded edges. The ropes move on conveyors while cutting blades divide them into individual lengths. The forming system gives the center its basic profile. A bounty center is not flat like a biscuit base. It is thick, soft, and slightly rounded. The shape matters because the chocolate coating must flow over it evenly. Sharp corners would make thin chocolate spots. Smooth edges help the shell cover the bar completely. After forming, the coconut centers move into a cooling or setting section. Cool air firms the binder. The bars become easier to handle. The center does not become hard. It simply gains enough structure to survive transfer, spacing, and chocolate coating. The bars pass through alignment guides. They must travel in straight lanes with equal gaps. Uneven spacing would cause problems in the enrober. Two bars touching each other could become stuck together by chocolate. A bar out of position could miss part of the coating curtain. Chocolate preparation runs separately from the coconut line. Cocoa ingredients, sugar, milk powder for milk. Chocolate versions, cocoa butter, and other fats are combined into a chocolate mass. The ingredients are mixed until they form a thick paste. This paste passes through refining rollers that grind the sugar and cocoa particles down to a fine size. Refining changes the texture from gritty to smooth. The refined chocolate then moves into conching equipment. Large mixing arms or rollers work the chocolate for a controlled period. The mass becomes smoother and more fluid as fat coats the dry particles. Heat and movement develop the final flow behavior needed for coating. Before the chocolate can cover the coconut bars, it must be tempered. Tempering controls the cocoa butter crystals. The chocolate is cooled, stirred, and gently warmed through a precise sequence. This creates stable crystals that allow the shell to set firm, smooth, and glossy. The tempered chocolate is pumped to the enrober. The coconut centers approach on a wire mesh belt. The belt carries them beneath a falling curtain of chocolate. As each center passes through the curtain, chocolate pours over the top and runs down the sides. At the same time, chocolate coats the underside. The mesh belt allows chocolate to rise or be applied from below, so the coconut center is sealed all around. Excess chocolate drains through the belt and returns to the circulation system. The coating is not finished immediately after the curtain. The bars pass under controlled air blowers. These blowers remove excess chocolate and smooth the shell. They also help define the final coating thickness. The airflow must be strong enough to even the surface, but not so strong that it exposes coconut. The soft shape of the coconut center affects how the chocolate moves. The coating flows more easily over rounded sides than over sharp corners. It gathers slightly at the base before excess drains away. The wire belt supports the bar while leaving only fine contact marks underneath. The coated bars may pass over a vibrating section. The vibration releases trapped air bubbles and helps chocolate settle evenly. Small ripples smooth out as the bar continues forward. The shell becomes continuous around the coconut core. Some bounty formats are twin bars. In those lines, centers may be formed and coated as individual fingers, then later paired inside the wrapper. The spacing system keeps the fingers separated until the wrapping stage. Each piece must have its own complete chocolate shell before pairing. The coated bars enter a cooling tunnel. Chilled air flows around them as they move slowly through the enclosed space. The chocolate begins to crystallize. The liquid shine becomes a firmer surface. The shell sets without melting the coconut center or drawing moisture outward. Cooling must be balanced. If the tunnel is too cold, chocolate can contract too sharply and crack. If cooling is too slow, the bars may mark or deform before wrapping. The line controls air temperature, humidity, belt speed, and residence time. Ferrero Rocher is manufactured by assembling a layered sphere where a roasted hazelnut sits inside a wafer shell. The shell is filled with hazelnut chocolate cream. Then the whole piece is coated in chocolate and rolled in chopped hazelnuts before a final set and wrap. The process starts with hazelnut preparation because nut size and roast level define the center bite and also influence how the coating adheres. Raw hazelnuts are cleaned with screens and air separation, so stones and shells are removed. The nuts are graded by diameter, so the center nut fits the wafer cavity without forcing cracks. Roasting line heats the nuts to a target color and moisture. Roasting drives off water and develops aroma while keeping the nut interior crisp. After roasting, the nuts are cooled quickly, so residual heat does not soften the wafer later. Skins are removed after roasting because loose skin fragments create bitter specks and interfere with cream texture. Nuts pass through rubbers or abrasive rollers that loosen skins. Air aspiration lifts skins away from the heavier nut kernels. The cleaned nuts are then rescreened to remove broken pieces. Whole nuts are routed to center insertion. Broken nuts are routed to chopped nut streams or paste production. A portion of the roasted nuts is chopped for the outer layer. Chopping is done with calibrated cutters that create a narrow size band. The target size must be large enough to read as crunchy pieces. The target size must be small enough to adhere evenly to a wet chocolate surface. Chopped nuts are screened to remove fines because fines create dust and dull the finish. The chopped nut stream is held in dry, conditioned air so it remains free-flowing. Another portion of the roasted nuts is processed into hazelnut paste for the cream and chocolate phases. Nuts enter a grinding system where rollers or stone mills reduce them to a smooth paste. Grinding generates heat, so the paste line uses temperature control to avoid over-thinning. The paste is refined until particle size is below the gritty threshold. The paste is then held in jacketed tanks with slow agitation to prevent oil separation. Wafer production runs as a separate stream because wafer must be crisp and dimensionally stable. Wafer batter is prepared by blending flour with water and sugar and small amounts of fat. Mixing is controlled to hydrate flour while limiting gluten development. The batter is filtered to remove lumps that would block depositor nozzles. Batter viscosity is adjusted so it spreads evenly on heated plates. Wafer baking uses wafer irons that form thin sheets by heating both sides. The batter is deposited onto the plates and spread into a uniform film. Heat drives water out quickly and sets the wafer into a rigid, porous sheet. Baking time is tuned so the sheet dries to low moisture without scorching. The sheet exits and is cooled so it becomes crisp and easy to cut. To create the rocher shell, the wafer is shaped into cups or hemispheres. One method presses warm wafer sheets into molded cavities and then trims the edges. Another method bakes wafer directly into formed shapes using shaped plates. Forming must avoid cracks because cracks allow cream leakage. The formed halves are inspected by size and by edge integrity. Wafer halves are then paired into hollow spheres. A joining step applies a thin line of adhesive cream or chocolate along the rim. Two halves are aligned and pressed together. Pressure is controlled so the seam closes without crushing the wafer walls. The joined shells are cooled briefly so the seam sets and the sphere stays rigid during filling. The filling cream is produced as a fat-based emulsion with suspended solids. Sugar and milk solids are blended with hazelnut paste and cocoa components depending on the target profile. The mass is refined so it becomes smooth and spreadable. Refining can be done with roll refiners or ball mills that reduce particle size. The cream is then conched or mixed under heat to remove moisture and to distribute fat. Final viscosity is tuned so it can be dosed into wafers without air gaps. Chocolate used for coating is prepared and tempered for stable crystallization. Chocolate is melted and filtered to remove unmelted particles. Tempering cools the chocolate and builds stable seed crystals. The chocolate is then brought to a working temperature that maintains flow. Viscosity is adjusted by temperature control and by cocoa butter balance. Stable viscosity is needed because coating thickness must be consistent. Filling the wafer sphere begins by dosing a layer of cream into the cavity. The dosing head inserts into the shell opening and dispenses a controlled volume. The shell rotates or indexes, so cream spreads along the inner wall. This creates a base that will hold the center nut. The volume is controlled to avoid excess that would squeeze out at closure. A whole roasted hazelnut is then placed into the center. Placement uses a singulation system that feeds nuts one by one. Each nut is aligned and dropped into the cream bed. The cream supports the nut and locks it in position. Nut placement must be centered so the final sphere balances during coating. Off-center, nuts create wobble and uneven chocolate thickness. After nut placement, the cavity is topped off with more cream. The second dose surrounds the nut and fills remaining void volume. The dosing profile is tuned to avoid trapping air around the nut. Air pockets can collapse during cooling and cause surface dents. The cream surface is leveled, so the opening can be sealed cleanly. Sealing closes the filled sphere, so the cream is enclosed. A wafer cap or a chocolate plug can be applied depending on design. If a wafer cap is used, it is bonded with a thin film of cream and pressed into place. If a chocolate plug is used, tempered chocolate is deposited to create a seal. The seal must be strong enough to survive later tumbling and coating. After sealing, the filled spheres are cooled to firm the cream. Cooling brings the fat phase into a stable crystal state. It also reduces cream tack, so spheres do not stick during transfer. Cooling is staged, so wafer does not absorb condensation. Humidity control matters because wafer crispness must be preserved. Once the centers are stable, the line moves into chocolate enrobing. The spheres pass through a chocolate curtain or a dipping system. Chocolate coats the surface and also acts as the adhesive for chopped nuts. Excess chocolate drains off as the spheres roll on a wire belt. A controlled vibration can smooth the coating and release trapped bubbles. Air knives can trim excess and define a consistent thickness. Immediately after chocolate coating, the spheres enter a nut coating stage. Chopped hazelnuts are applied while the chocolate is still wet. The spheres roll through a bed of chopped nuts, or nuts are showered from above. Rolling ensures full coverage across the sphere. Nut feed rate is tuned, so coverage is dense but not clumped. Excess nuts fall away and are recirculated after screening. Nut adhesion depends on chocolate temperature and set speed. If chocolate sets too fast, nuts will not embed fully and will shed later. If chocolate sets too slow, nuts can slide and form bare patches. The process balances chocolate temper and cooling tunnel entry so the surface remains tacky long enough for nut embedding. After nut application, the pieces enter a cooling tunnel that solidifies the chocolate. The cooling profile is staged to promote stable crystals. Early cooling sets the surface quickly, so nuts lock in place. Later cooling pulls heat out, gradually, to avoid contraction cracks. Final exit temperature is set, so pieces are hard enough for wrapping. During cooling, the internal cream also equilibrates. The cream-fat network continues crystallizing and becomes firmer. This improves bite and reduces oil migration. Temperature stability prevents bloom risk and keeps the outer finish glossy. The wafer remains protected because the chocolate and cream act as moisture barriers. Some lines apply a final polish to reduce loose nut dust. A gentle tumbling or airbrushing step can remove unattached fragments. This step improves pack cleanliness and reduces debris in wrappers. It also reduces scuffing during downstream handling. Sorting and inspection occur before packaging. Vision systems can detect incomplete nut coverage and shape defects. Weight checks confirm fill and nut presence. Rejects are diverted so only uniform pieces reach wrapping. Metal detection can be used as a final integrity control. Reese's peanut butter cups are manufactured by building two materials that behave in opposite ways and then forcing them to meet cleanly at high speed. The chocolate must flow like a liquid in the depositor, then crystallize into a rigid shell that releases from tooling. The peanut center must be soft enough to bite with a short crumble, yet stiff enough to hold shape, resist oil separation, and accept a top seal without squeezing out. The peanut component begins with roasted peanuts that are converted into a paste with tightly controlled temperature. Incoming kernels are cleaned and screened, so shell fragments and fines are removed before grinding. Roasting level is chosen to drive down moisture and develop aroma while keeping oil stable. After roasting, the nuts are cooled quickly so residual heat does not thin the paste and accelerate oil separation during storage. Grinding is staged because peanut butter texture depends on particle size distribution and shear history. A coarse grinder breaks kernels and releases oil, creating a continuous fat phase. A second grinder refines particles to the desired smoothness. Friction heats the paste, so grinders are jacketed or throughput is controlled to keep temperature in a narrow range. If the paste warms too much, it becomes overly fluid and later produces a filling that flows and smears. If too cool, it becomes stiff and resists blending with dry powders. The paste then moves into filling formulation. The goal here is not a spreadable peanut butter, but a depositable confection that sets with a slightly crumbly bite. Fine powdered sugar is the main structure builder. It is sifted so clumps are removed because clumps create dry pockets and inconsistent dosing. Salt and flavor components are prepared as micro additions. A compatible fat stream may be used to tune firmness and melt profile, and emulsifiers are staged to stabilize the oil phase and improve flow through depositors. Mixing is done in high torque equipment because the peanut paste thickens dramatically as powders are added. The paste enters first, then powders are introduced in a controlled feed so the mix wets gradually rather than forming dry rafts. As sugar absorbs free oil, the mass becomes less glossy and more plastic. Mixing energy is tuned to avoid turning the mass into a smooth, homogeneous paste. Too much shear breaks the short structure and yields a slick filling that feels less crumbly. Too little shear leaves dry streaks and causes weak spots that crack under the chocolate cap. Temperature control during filling mixing is a core lever. The mass must be warm enough that it can be pumped and metered, but not so warm that it relaxes and spreads inside the cup. Jacketed mixers and conditioned hoppers hold the filling in a narrow temperature band. The filling is often moved through a short conditioning step after mixing so fat crystals can begin forming and the texture becomes more consistent. This conditioning also allows entrained air to rise out. Large bubbles create voids that later collapse and cause dents in the top surface. While the filling is being prepared, the chocolate system is built for shell formation. Chocolate is melted, filtered, and held at a stable temperature, so viscosity is constant. The key operation is tempering, which establishes a controlled population of stable cocoa butter crystals. Tempered chocolate behaves like a fluid at the depositor, but solidifies quickly into a glossy, firm structure. Tempering is maintained by staged cooling and reheating within a continuous unit, with sensors watching temperature and flow resistance as indirect signals of crystal content. The forming line starts with paper liners. Liners are denested and placed into cavities on a moving mold plate. Cavity fit is controlled because the liner must be supported to prevent wrinkling when chocolate is spun. Liner placement accuracy matters because a shifted liner creates thin shell walls on one side and thick walls on the other, which leads to breakage during demolding and uneven bite. Shell formation is done by depositing a metered shot of tempered chocolate into each lined cavity and then immediately shaping it into a cup. The shaping step is usually a spin or a combination of spin and vibration. Spinning forces chocolate up the liner walls and leaves a hollow center. Spin time and speed define wall thickness and rim height. If the spin is too aggressive, walls become too thin and crack later. If too gentle, the shell becomes heavy and reduces space for filling. Vibration during or after spinning helps remove bubbles and smooth the interior surface. The newly formed shells enter a brief cooling zone. This is not full hardening. It is a partial set that makes the shell self-supporting but still receptive to bonding with the filling. Cooling must be controlled because an overly cold shell can create poor adhesion and delamination. An overly warm shell can deform when filling is deposited and can create uneven rim geometry. Filling deposition is engineered to place a consistent puck inside the shell without contaminating the rim. The filling is delivered from conditioned hoppers to deposit heads that meter precise volumes. Depositing can be a single shot that forms a dome or a spiral that levels more evenly. The deposit height is controlled so there is clearance for the chocolate top. If filling touches the rim, it interferes with sealing and creates weak edges. Many lines use a light vibration or a short dwell to let the filling settle into a consistent profile. But the motion must be gentle because too much vibration can smear filling into the shell wall and create uneven thickness. Top sealing is created by depositing a second shot of tempered chocolate. The chocolate must flow outward enough to meet the shell rim and form a continuous bond. Deposit volume sets top thickness. Too thin a top can crack during handling. Too thick a top dominates bite and slows cooling. Some lines apply a short vibration after topping to level the surface and release trapped air. This vibration is tuned to avoid chocolate climbing the liner edge and creating flash. Once topped, the cups enter the main cooling tunnel. Cooling is staged because chocolate crystallization must be guided into a stable form. The first zone sets the surface quickly to prevent smearing and to lock the top shape. Subsequent zones cool more gradually so the entire chocolate mass crystallizes uniformly without internal stress. Exit temperature is chosen so the cups are rigid enough to demold and convey without scuffing. During cooling, the filling also stabilizes. Fat crystals within the peanut mixture continue forming and the filling becomes firmer and more brittle in its short structure. This is essential for the characteristic bite. If the filling remains too soft, it will squeeze under pressure and cause top separation. If it becomes too hard, it loses the expected crumble and becomes a dense block. Demolding releases the lined cups from the mold plate. Release depends on correct temper and correct cooling because the chocolate must contract slightly away from the cavity walls. Gentle ejectors or inversion steps drop the cups onto belts. Handling is kept low impact because rims can chip and liners can crease. Once on the belt, cups can pass through inspection stations. Vision checks can detect missing tops, off-center fills, and liner misplacement. Weight checks confirm dosing accuracy and flag missing deposits. Packaging is designed around preventing temperature rise and abrasion. Individual cups are often flow wrapped. Wrapping film is formed around each cup and sealed with controlled heat and dwell time. Heat must be sufficient to seal film without warming the chocolate surface enough to mark. Film tension is controlled so it does not crush the cup. For multi-pack formats, cups are collated into trays or sleeves that prevent movement and protect rims. Cartoning then adds stiffness and stack strength. Case packing arranges cartons to reduce compression and minimize vibration that could crack chocolate edges. Skittles are manufactured by making a chewy center that behaves like a resilient pellet, then growing a hard sugar shell around that pellet in hundreds of small additions, then adding color and a final finish so every piece looks identical and moves cleanly through packaging. The center is engineered first as a thermoplastic candy rather than as a syrup. Sugar and glucose syrup are treated as structural ingredients that control glass transition and chew. Granulated sugar is screened so crystal size stays consistent and dissolution is predictable. Glucose syrup is held warm in jacketed tanks so it meters smoothly and does not pulse. Water is filtered and tempered because small temperature changes affect the cook profile. Acids and salts are staged as micro additions because they influence both flavor and how the cooked mass behaves during conditioning. A dissolving step makes a clear feed syrup. Sugar and water are mixed under heat with strong agitation until no grain remains. Any undissolved grain would later seed crystallization and create weak spots in the center. The clear syrup then enters a continuous cooker or batch cooker where it is concentrated to a high solids level. Heat input is rapid to minimize time at elevated temperature because long heat exposure darkens sugars and shifts texture. In many lines, the syrup is heated under pressure and then finished with a flash step that removes water quickly and tightens final moisture. Cook endpoint is chosen to produce a mass that can be shaped without sticking and without cracking. If moisture is too high, pellets deform and flatten during later tumbling. If moisture is too low, pellets become brittle and can fracture under coating impacts. The cooked base is therefore delivered to a cooling stage that drops temperature to a range suitable for adding sensitive components. Flavor for the center is not the same as the final flavor experience because much of Skittles' character is carried by shell and aroma at the surface. Even so, the center is commonly given a base flavor note and a consistent sweetness profile. Flavors are injected after the hottest zone to preserve volatiles. Acids may be split between center and shell strategy. A portion of acid can be added late to set a baseline tartness without weakening the center structure. Mixing downstream uses static mixers or low shear manifolds to avoid entraining air. The cooked mass then becomes a plastic dough and enters forming. Forming begins by pushing the mass through an extrusion head that produces ropes at a fixed diameter, or by delivering it directly to a pellet former, depending on equipment design. Rope diameter is a major variable because shell thickness is added on top, so the core size must stay tight to hit final piece size. A synchronized knife cuts the rope into pellets. Cut timing is locked to belt speed, so pellet mass stays consistent across the run. Fresh pellets have cut faces and a warm surface. They are transferred immediately to a rounding stage where they tumble and roll. Rolling knocks off sharp edges and produces the characteristic rounded shape that will coat evenly. This stage also seals micro cracks at the surface by gentle friction warming. Rounding is tuned to avoid smearing because smearing creates flats that later show as uneven shell thickness. After rounding, the cores go through conditioning. Conditioning is a controlled cooling and rest that stabilizes temperature and moisture through each core. The cores must be firm enough to withstand repeated coating cycles, but the surface must still accept initial shell adhesion. Conditioning airflow and temperature are set so surfaces are dry to the touch, while the interior retains the desired chew. Shell building is performed in rotating coating pans or perforated drums. The drum creates a rolling bed of cores that continuously cascades. Cascade behavior is controlled by fill level and rotation speed. A stable cascade ensures every core sees the same exposure to syrup spray and drying air. If the bed slides rather than rolls, pieces develop flat faces and shell becomes uneven. The first shell layers are engineered as a bonding bridge. A relatively light syrup is sprayed in short pulses. Droplet size is kept fine, so the film spreads thinly and evenly. Dry air immediately follows to evaporate water and begin crystallization. These early coats must set quickly to prevent pieces sticking together, and they must not add enough water to soften the core surface. Once the first layers lock on, bulk shell growth begins. A higher solid syrup is sprayed, and fine sugar is often dusted onto the wet surface. The dust absorbs moisture and accelerates set while increasing build rate. Airflow then dries the layer and forces crystallization. This spray, dust, and dry cycle is repeated many times. Each cycle adds a tiny increment of thickness, so stress remains low and cracks do not form. Drying is the most sensitive control in shell growth because it governs how crystals form within each layer. If drying is too fast, the surface can harden while moisture remains inside the layer, creating a trapped core that later pits or fractures. If drying is too slow, the surface stays tacky and pieces can twin. Twin formation is prevented by matching spray volume to drying capacity and maintaining continuous rolling so wet surfaces do not remain in contact. As thickness increases, the process shifts to smoothing. Powder addition is reduced, and the system relies more on thin syrup films that flow into micro valleys. Longer dry times then lock a smoother surface. Smoothness matters because it improves shine and prevents scuffing, and it provides a better substrate for printing. Color is applied as a sequence of thin coats rather than a single heavy dye layer. Color solutions are prepared to precise concentration and filtered so no particulates enter spray nozzles. Color is introduced when shell thickness is near target, so pigment remains close to the surface and looks bright. The drum receives a light color spray, then drying air sets it fully. Multiple passes build saturation evenly. Heavy color application would pool and create blotches, especially where shell microtexture is still present. Because Skittles are produced in multiple colors, runs are typically separated by color. Each color run uses its own color dosing and its own endpoint checks. Between colors, spray circuits are flushed to prevent cross tint. Shade is monitored by optical measurement on samples, and adjustments are made by changing pass count or concentration rather than by altering the underlying shell build. After color, clear finishing coats can be applied to improve durability and reduce rub-off. These coats are very light and followed by longer drying to reach a stable moisture endpoint. Moisture endpoint is critical because a slightly damp shell scuffs and sticks, while an overly dry shell can become brittle and chip under impact. The letter marking is applied near the end of finishing. Printing uses edible ink, transferred by a pad or similar contact method. Pieces are fed into a system that presents a stable face and applies the mark. Surface condition at this moment matters. The shell must be smooth and dry so the ink bonds and does not smear. A short drying stage follows, so the mark sets before pieces rub against each other. Polishing is the final surface operation. A very small amount of polishing agent is misted onto the tumbling pieces. The film spreads through contact and fills micropores, increasing gloss and reducing friction. Reduced friction helps pieces flow through packaging machines and reduces scuffing in bags. Polishing is controlled carefully because excess film can feel waxy and can interfere with print clarity. After polishing, the pieces are conditioned briefly to equalize moisture and temperature. Equalization reduces internal stress in the shell and improves resistance to fine cracking. Screening then removes fines, broken pieces, and twins that escaped earlier control. Size classification can be used to remove out-of-band pieces that would stand out in packs and behave differently in weighers. Packaging begins with gentle conveying into multi-head weighers. The pieces must flow freely without bridging. Hopper design and surface finish reduce sticking. The weigher selects combinations of small hopper dumps to hit target weight quickly. The portion drops into a form fill seal machine, where film is formed into a tube and sealed above and below the product drop. Seal timing is set so candies do not lodge in the seal zone. Clean seals are essential because moisture ingress softens shells and dulls gloss. For tube or carton formats, dosing can be by count or by volume, but the same requirement applies. Piece size distribution must be tight so count accuracy stays high, and so packs feel consistent. After filling, closures are applied and coating is printed. Packs are checked for weight and seal integrity, then case packed. Milka chocolate is manufactured by turning cocoa and dairy ingredients into a low moisture, fat continuous suspension with a very narrow particle size range, then setting that suspension into bars through precise crystal control and staged cooling. The line begins by stabilizing dairy inputs because milk solids introduce both flavor and a strong sensitivity to water. Milk arrives as powder, concentrate, or a pre-processed dairy ingredient depending on the plant setup. Powdered streams are sieved to break agglomerates because compacted milk lumps do not disperse evenly and later show up as grainy flecks. If liquid dairy or concentrate is used, it is filtered and held at controlled temperature, so viscosity and dosing remain stable. Sugar is handled as a dry engineered solid, screened for consistent crystal size, because crystal size determines refining load and final mouthfeel. Cocoa components enter as cocoa liquor, cocoa butter, and sometimes cocoa powder. Cocoa liquor is kept warm so it stays pumpable, while cocoa butter is melted and filtered so it meters cleanly. A key upstream objective is removing free water from the system early because water drives chocolate thickening and unstable flow. When the process uses a crumb route, milk and sugar are combined and cooked into a dry matrix before they ever meet the final chocolate fats. The milk-sugar mixture is heated under controlled mixing, so sugar dissolves and water evaporates. As water leaves, the mix transitions from syrupy to granular, and then to a dry crumb. Endpoint is set by moisture content and by how the crumb fractures. Too wet yields a crumb that later makes chocolate seize and thicken. Too dry yields excessive browning and harsh cooked notes. Once the crumb reaches endpoint, it is cooled and milled to a manageable particle size, so it blends uniformly downstream. If the process does not use a crumb route, the same moisture goal is achieved by strict control of powder moisture and by downstream conching, but the plant still treats water as the enemy of stable rheology. All ingredient handling and air exposure is therefore designed to keep humidity pickup low. Mixing creates the first chocolate mass. Cocoa liquor and a portion of melted cocoa butter enter a mixer to form a fluid fat phase. Crumb or milk solids and sugar are then introduced gradually, so particles become wetted rather than floating as dry islands. The mixer uses high torque and wall scraping because the mass is thick at this stage. The target is a uniform paste where solids distribution is even and there are no dry pockets. This paste is not yet smooth, but uniformity here prevents downstream refining streaks. Refining is where smoothness is physically created. The paste is fed to roll refiners or an equivalent milling system that reduces particle size into the low tens of microns. Roll refining squeezes the mass through a series of narrowing gaps, breaking sugar crystals and milk solids into smaller particles. The output leaves the final roll as thin flakes. These flakes have very high surface area and very little free fat at their surfaces, so they behave dry and dusty unless they move quickly into the next stage. Conching transforms refined flakes into a stable flowing chocolate by completing fat wetting and removing trace moisture. In a conch, paddles or rotors knead the chocolate under controlled heat. Mechanical work breaks down remaining agglomerates and forces cocoa butter to coat every particle. Heat keeps fats fluid, while airflow carries away moisture and volatile compounds. Moisture removal is not optional because even a small amount of water pushes viscosity up sharply. Conching is therefore run as a controlled balance between temperature, shear, and venting, so the mass becomes fluid without overheating. During early conching, the mass can appear crumbly and resistant because particle surfaces are not fully wetted. As conching continues, friction drops and the mass becomes glossy and pumpable. Viscosity and yield stress are the process indicators because they determine whether the chocolate will deposit cleanly into molds and whether it will release cleanly after cooling. Emulsifiers are introduced late in conching to fine-tune flow. Lecithin reduces yield stress by improving particle wetting. Additional flow modifiers can be dosed to reduce viscosity further at the same fat content. Dosing is precise because tiny changes alter curtain behavior, depositor accuracy, and final snap. Once conched, the chocolate is held in tempered storage tanks at a stable temperature with gentle agitation. Filtration removes any unmelted lumps or foreign particles before tempering. At this point, the chocolate is chemically and physically ready, but its fat crystals are not yet in the correct form for molding. Tempering is the controlled crystallization step that makes the final bar glossy, hard, and stable. Cocoa butter can solidify into multiple crystal forms, but only specific forms produce the desired contraction and snap. Tempering machines first heat the chocolate enough to melt all existing crystals. They then cool it under agitation so crystals nucleate. The chocolate is then reheated slightly to melt unstable crystals while leaving stable seed crystals. The output is a chocolate that remains fluid at the working temperature but contains a measured population of stable seeds. This seeded chocolate feeds molding. Molds are cleaned and temperature conditioned so the surface is dry and does not shock the chocolate. Deposit heads meter chocolate into each cavity with tight mass control. Immediately after deposit, molds pass over vibrating tables. Vibration releases trapped air bubbles and levels the surface so the bar face is smooth. Vibration also helps chocolate flow into fine embossed details if the mold carries a design. Cooling tunnels then set the chocolate. Cooling is staged because the goal is to crystallize the entire bar without creating stress. The first zone sets the surface quickly so it holds shape. Subsequent zones cool more gradually so stable crystals grow through the thickness. If cooling is too fast, internal stress can lead to cracks or later bloom. If cooling is too slow, throughput drops and the chocolate may stay soft long enough to pick up marks. Air humidity is controlled in the tunnel to prevent condensation because moisture on the surface can cause sugar bloom and dullness. As the bar cools, it contracts slightly. This contraction is essential for demolding. Correct temper and correct cooling create a bar that releases cleanly when the mold is inverted or flexed. After release, bars move onto conveyors that minimize scuffing. Any surface abrasion at this stage will remain visible after wrapping. Inspection can be integrated immediately after demolding. Vision checks can detect surface voids and broken corners. Weight checks confirm deposit accuracy. Bars outside tolerance are diverted. Reworked chocolate is collected and remelted, then returned upstream in controlled proportions so it does not destabilize tempering. Wrapping protects the finished bars from moisture, oxygen, and physical marks. Bars are indexed into wrapping machines that fold film or foil around them. Fold geometry is controlled so the wrap sits tight without crushing edges. Heat sealing parameters are tuned to close the film without warming the bar enough to soften the surface. Coating is applied for traceability and packs are checked for seal integrity. Cartoning and case packing follow for multi-unit formats. Cartons provide stacking strength and protect wrapped bars from puncture and abrasion. Cases are built and sealed for transport. Storage temperature stability is maintained to protect the cocoa butter crystal network because temperature swings can encourage bloom and soften snap. Adidas soccer balls spin beneath enormous hydraulic presses as layers of synthetic material fuse together under carefully controlled heat and pressure, transforming flexible sheets into panels strong enough to survive thousands of powerful impacts. The press opens only seconds later, revealing perfectly formed pieces that look deceptively simple. Yet every curve, every texture, and every fraction of a millimeter has already been engineered for what comes next. Those flat panels are still nowhere close to becoming a finished ball. Before a single kick could ever send one soaring through the air, the factory must build an internal structure capable of maintaining its shape through relentless compression, and that hidden construction begins long before the outer shell is ever assembled. Production starts with large rolls of synthetic polyurethane material arriving at automated unwinding stations. Unlike natural leather used decades ago, modern performance soccer balls rely on multi-layer composites engineered for durability, water resistance, flexibility, and consistent flight characteristics. Each roll feeds into precision laminating equipment where several functional layers are bonded together into one continuous sheet. Beneath the visible outer surface, textile reinforcement fabrics, polymer foams, and adhesive films combine into a structure that balances softness with remarkable strength. Heated rollers compress every layer together while maintaining identical thickness across the full width of the material, ensuring every future panel behaves exactly like the next. As the laminated sheets move forward, another operation quietly prepares one of the ball's most important characteristics. Embossing rollers covered in microscopic surface patterns press against the material, creating thousands of tiny textures across every panel. Some patterns consist of shallow dimples, while others use intricate geometric shapes depending on the ball's intended performance. These textures influence how air flows across the finished ball during flight, helping stabilize movement while also improving grip. Although the changes appear subtle, the surface geometry created here plays an important role long after the ball leaves the factory. The embossed sheets now approach high-speed cutting systems equipped with hardened steel dies. Instead of simply producing circles or squares, these presses stamp out precisely engineered panel shapes that fit together with extraordinary accuracy. Depending on the model, the dies create traditional pentagons and hexagons, or more advanced panel geometries designed specifically for modern aerodynamic performance. Every stroke of the press produces another complete set, while computerized positioning systems minimize waste between adjacent cuts. Scrap material never remains unused for long. Recovery systems collect it automatically before directing it toward recycling processes where it can contribute to future production. Once separated, the panels travel toward printing stations that transform the plain synthetic surface into the instantly recognizable appearance associated with premium soccer balls. Large format industrial printing equipment applies graphics, logos, registration marks, and intricate color designs with remarkable precision. Some production lines use advanced digital printing, while others rely on multi-stage screen printing depending on design complexity. Between each color application, controlled drying systems stabilize the inks before the next layer arrives. What began as plain white synthetic material gradually develops into vivid geometric artwork that wraps seamlessly across the finished sphere. The printed panels continue into inspection systems, where high-resolution cameras examine every piece individually. Color consistency, print, alignment, dimensions, surface texture, and edge quality are verified automatically before the panels move onward. Pieces showing incomplete printing, dimensional variation, or surface defects are diverted immediately without interrupting the production flow. Only perfectly formed panels continue toward assembly, because even minor inconsistencies become much more noticeable once the ball takes shape. While the outer shell components move through inspection, another production line prepares the internal bladder that gives the ball its elasticity. High-grade butyl or natural latex compounds begin as carefully blended rubber mixtures prepared inside enclosed mixing equipment. Massive internal mixers knead the rubber under controlled temperatures until every ingredient disperses evenly throughout the compound. Carbon black, stabilizers, curing agents, and elastic polymers all contribute specific mechanical properties, ensuring the finished bladder retains air efficiently while remaining flexible through repeated inflation and impact. The rubber compound leaves the mixers and passes through extrusion equipment, where it forms continuous tubes of carefully controlled thickness. Sections are cut automatically before entering heated molds that shape them into hollow spherical bladders. Inside the molds, heat and pressure initiate vulcanization, permanently cross-linking the rubber molecules into an elastic structure capable of expanding repeatedly without permanent deformation. Once curing finishes, the bladders cool gradually before inflation valves are installed through precision insertion equipment. Every bladder receives an initial inflation test immediately afterward to verify airtight performance before continuing. Now, two completely separate manufacturing streams finally begin moving toward one another. The finished bladder enters temporary inflation stations, where compressed air gives it enough shape to support shell assembly. Nearby, workers or automated positioning systems begin arranging the printed outer panels around the inflated core according to the exact geometric layout required for the finished ball. Although the synthetic shell appears flat only moments earlier, each panel now starts curving naturally as it wraps around the expanding bladder. Depending on the production method, assembly follows one of two highly engineered paths. For thermally bonded premium balls, precisely positioned panels enter specialized molding systems where heat-activated adhesives permanently fuse adjoining edges together. Hydraulic molds surround the partially assembled ball, while carefully controlled temperature and pressure activate the bonding layers hidden beneath the outer surface. Rather than relying on visible stitching, the panels become one continuous, waterproof shell with exceptionally smooth seams. This process creates remarkable dimensional consistency while reducing water absorption during play. For stitched models, automated pre-punching equipment prepares every panel edge before high-strength polyester threads begin joining neighboring sections. The stitching sequence follows a carefully planned order that gradually encloses the inflated bladder inside the growing shell. Each stitch must maintain consistent tension throughout the ball because uneven stitching could alter both shape and durability. The final seam closes only after the bladder has been fully enclosed, completing the spherical structure for the first time. Although the ball now looks finished, another major transformation still waits ahead. Every assembled ball enters calibration stations where controlled inflation raises internal pressure to its specified level. Precision gauges monitor air pressure continuously while rotating support systems keep the ball perfectly centered throughout testing. The shell stretches slightly as pressure increases, allowing every panel to settle into its final position. Tiny adjustments made here influence how uniformly the ball responds when struck at high speed. The inflated balls continue into heated shaping molds that perform one final geometric correction. Even carefully assembled panels may contain microscopic variations before molding. Inside the shaping press, heat and pressure gently encourage every seam and panel to conform to the exact spherical dimensions programmed by the manufacturer. When the molds open again, each ball displays remarkably consistent diameter and roundness, creating the foundation for predictable flight characteristics. Now the quality control process becomes especially demanding. Every ball rolls individually beneath laser measurement systems capable of detecting extremely small deviations in circumference, roundness, and panel alignment. Computer-controlled cameras inspect print registration from multiple angles, while automated rotation allows every section of the surface to be examined. Balls showing dimensional irregularities, cosmetic defects, or seam inconsistencies leave the production line automatically. Those meeting specification continue toward another series of demanding evaluations. Impact testing begins inside mechanical kicking machines where pneumatic launch systems repeatedly strike inflated balls with carefully controlled force. Some machines fire the balls against rigid surfaces hundreds or even thousands of times, while sensors monitor rebound behavior and structural stability. Nearby compression equipment repeatedly squeezes other samples to simulate extended play. Additional pressure testing stations monitor long-term air retention, ensuring the bladder and valve continue performing after repeated impacts. Only after surviving these evaluations does production move toward its final stages. Accepted balls pass through cleaning stations where soft rotating brushes remove any remaining manufacturing residue from the outer surface. Gentle polishing systems restore a uniform finish while preserving the embossed texture created much earlier during lamination. Bright inspection lighting reveals the completed appearance for the first time, allowing automated cameras to perform one final visual verification before packaging begins. Packaging starts as automatic deflation equipment reduces internal pressure slightly, allowing the balls to occupy less space during transportation while protecting the shell from unnecessary stress. Depending on the retail format, some models remain partially inflated while others are folded gently into compact packaging. Printed cartons, protective bags, or display boxes arrive from parallel packaging lines where robotic loading systems position every ball precisely inside. Instruction leaflets, inflation information, and identification labels are added automatically before the packages are sealed. Completed retail packages continue towards secondary packaging where corrugated shipping cartons open automatically from flat blanks. Robotic handling equipment loads the programmed number of packaged soccer balls into every carton before folding mechanisms close the upper flaps. Hot melt adhesive secures each seam while compression conveyors maintain square geometry until the adhesive cures completely. Machine vision confirms carton integrity, product count, and coding before every case advances toward the warehouse. Coca-Cola disappears into an empty bottle before anyone ever sees the most important transformation, because by the time the liquid reaches the filling machine, nearly every critical step has already happened behind sealed stainless steel walls. The beverage rushing toward the filler is already cold, already carbonated, and already balanced to its final drinking strength. It travels through polished pipelines under carefully maintained pressure, moving quietly despite carrying millions of dissolved carbon dioxide molecules that are waiting for a chance to escape. Every valve, every bend, and every pump between the blending room and the filling carousel has one responsibility: protect that carbonation. A sudden pressure drop would instantly create foam, waste product, and destroy fill accuracy. The entire production line is built around preventing that from happening, but to understand why, the process has to rewind to where Coca-Cola begins as nothing more than treated water and concentrated syrup. Water enters the factory continuously through large stainless steel supply lines before passing into an extensive treatment system. Since water makes up the overwhelming majority of every bottle and can, consistency is everything. The incoming supply first moves through coarse filtration that removes suspended particles before entering activated carbon filters that eliminate unwanted tastes and odors. Depending on the facility, additional polishing systems refine mineral balance and clarity even further. Storage tanks hold this purified water under controlled conditions until production demands it. Although the water appears unchanged to the eye, it has become a carefully standardized ingredient capable of producing identical batches every hour of every day. While treated water waits in storage, another process unfolds in the syrup room. Massive blending vessels begin filling with measured quantities of sweetener. If granulated sugar is used, controlled feeding systems deliver it steadily into circulating water. The crystals disappear as powerful agitators rotate beneath the surface, creating a dense syrup that grows thicker with every passing minute. In facilities using liquid sweetener, insulated pipelines deliver the ingredient directly into the tanks, while electronic flow meters continuously verify every addition. Regardless of the sweetener source, the objective remains identical: create a perfectly uniform foundation before a single drop of flavor concentrate enters the mixture. The syrup becomes glossy, heavier than water, and completely free of undissolved solids before moving forward. Only after the sweet base reaches the required consistency does the next stage begin. Concentrated Coca-Cola flavor is introduced through enclosed dosing systems designed for exceptional precision. Compared with the volume of sweet syrup already inside the tank, the concentrate represents only a small fraction of the batch, yet it transforms everything. Dark ribbons briefly appear as the concentrate enters the circulating liquid before disappearing into the constantly moving current. The color deepens almost immediately, changing the once clear syrup into a rich brown concentrate. Acidity, color, and the signature flavor profile spread throughout the vessel until every portion matches every other. Even now, however, the mixture bears little resemblance to the finished drink because it is still far too concentrated to consume. The completed syrup moves into insulated holding tanks equipped with slow-turning agitators. These paddles are intentionally gentle. They keep ingredients evenly distributed without introducing unnecessary air into the mixture. Sensors constantly monitor temperature, liquid level, and transfer rates, while automated pumps respond whenever the production line requests more concentrate. On the opposite side of the blending system, treated water begins its own journey toward the proportioning unit. Two completely separate streams now travel toward a single destination, and this is where the beverage finally begins taking its recognizable form. Inside the proportioning system, electronic flow meters monitor both liquids continuously. One stream carries dense concentrated syrup, while the other carries crystal clear treated water. Computer-controlled valves make tiny adjustments hundreds of times each minute, compensating for changing production speeds without allowing the ratio to drift. The two liquids meet inside enclosed blending chambers, where the syrup disperses almost instantly throughout the much larger water stream. Within seconds, the beverage reaches its finished sweetness, acidity, color, and flavor intensity. It finally tastes like Coca-Cola, but something essential is still missing. At this point, the liquid is completely flat. There is no sparkle, no hiss, and none of the crisp sensation associated with opening a fresh bottle. Before carbonation can begin, temperature must change dramatically. The beverage enters a plate heat exchanger constructed from stacks of thin stainless steel plates. Cold coolant flows along one side of each plate while the beverage flows along the other, allowing heat to transfer rapidly through the metal without the two liquids ever mixing. Within moments, the drink exits several degrees colder than when it entered. This cooling stage is critical because cold liquid absorbs carbon dioxide far more effectively than warm liquid while also reducing foam during filling. Hidden inside this seemingly simple temperature change is one of the biggest factors determining how lively the finished beverage will feel. Many production lines include another important step before carbonation begins. Dissolved oxygen and unwanted gases are removed through deaeration equipment operating under carefully controlled conditions. Tiny air bubbles separate from the liquid before escaping through the system, leaving behind a beverage better prepared to accept carbon dioxide. Although invisible to anyone watching the conveyor outside, this stage improves carbonation performance and helps preserve long-term flavor stability. Only after chilling and deaeration does the beverage finally approach the machine responsible for one of the factory's most dramatic transformations. Inside the carbonator, chilled Coca-Cola meets carbon dioxide under pressure. The gas enters through specialized diffusers that create enormous surface area while maintaining complete control over pressure and flow. Instead of forming visible fizz, the gas dissolves directly into the liquid. The beverage leaving the vessel looks almost identical to the flat drink that entered moments earlier, yet internally, everything has changed. Millions of microscopic carbon dioxide molecules are now held inside the cold liquid under pressure, waiting for the instant that pressure disappears. From here onward, every section of the production line focuses on preserving those dissolved gases until the package is completely sealed. At exactly the same time, empty containers begin their own journey toward the filler. Plastic bottles usually start as compact PET preforms that resemble thick test tubes with finished bottlenecks already molded into place. These preforms travel through infrared heating ovens, where they rotate continuously, allowing heat to soften only the body while leaving the threaded neck cool and dimensionally stable. Once heated, each preform enters a blow mold, where a stretch rod pulls downward through its center, while high-pressure compressed air expands the softened plastic against chilled mold walls. In only a few seconds, the compact preform becomes a full-sized Coca-Cola bottle, complete with base contours, shoulder profile, grip panels, and label area. Aluminum cans follow a completely different route. Already formed and printed before arriving at the beverage plant, they are unloaded from pallets by automated depalletizers before entering high-speed conveyors. Every empty can passes through a rinsing station where filtered air or treated water removes dust and loose particles. Bottles undergo similar internal cleaning after blow molding, ensuring every container reaches the filler clean and ready to receive the finished beverage. Now both production streams finally meet at the rotary filling machine. Empty bottles and cans enter through synchronized star wheels that position each container beneath an individual filling valve. The filler itself rotates continuously while maintaining pressure inside its enclosed bowl. For bottles, the valve seals tightly against the neck opening before internal pressure equalizes with the pressure inside the filler. This single step prevents dissolved carbon dioxide from escaping violently as filling begins. Once pressure is balanced, the valve opens and Coca-Cola flows smoothly into the container. The dark liquid rises rapidly while only a carefully controlled amount of foam forms near the surface. Sensors monitor fill height precisely before each valve closes at exactly the programmed level. The filled containers move immediately toward closure because every fraction of a second matters once carbonation has entered the package. Plastic bottles receive caps supplied through vibrating sorting bowls that orient every closure correctly before feeding rotating capping heads. Each cap tightens to a carefully controlled torque that seals carbonation securely without damaging bottle threads. Aluminum cans instead travel into seamers, where lids drop into position before precision rollers fold the lid, curl around the can flange. Two separate roller operations create the finished double seam, mechanically locking multiple layers of aluminum together into a pressure-resistant seal without requiring adhesive. Inspection begins immediately after sealing. Vision systems examine fill height, cap alignment, tamper bands, seam quality, dents, scratches, and container deformation, while laser sensors verify liquid levels. Automated reject systems remove any package falling outside specification without slowing production. Cold filling leaves moisture condensed across container surfaces, so powerful air knives blast away water before labeling and secondary packaging begin. Plastic bottles move through labeling equipment where printed film unwinds continuously from large reels. Registration sensors track alignment marks before rotary knives cut individual labels. Adhesive secures the leading edge while spinning bottles wrap the remaining label tightly around their bodies. Pressure rollers smooth every wrinkle before the bottles continue toward coating. Shrink sleeve formats instead receive loose sleeves that tighten around the bottle inside heated tunnels, perfectly matching every contour as the film contracts. The final stages transform individual containers into retail-ready products. Guide rails divide the conveyor into multiple lanes before timing screws establish exact spacing for grouping. 6-packs, 12-packs, and larger configurations form automatically before shrink film or paperboard cartons surround the containers. Heat tunnels tighten shrink film into compact bundles, while cartoning equipment folds and seals printed paperboard around grouped bottles or cans. Every finished pack passes another inspection stage, verifying count, orientation, coding, and package integrity before entering corrugated shipping cases. Starburst pours from a heated candy cooker as a thick, glossy ribbon, flowing onto temperature-controlled equipment where it begins losing heat almost immediately. At this point, there are no neat squares and no individual wrappers, only a continuous fruit-flavored mass that bends and stretches as rollers pull it forward. Within a short distance, This flowing confection will become a precisely measured slab, then narrow ropes, then thousands of identical bite-sized pieces. But cutting soft candy cleanly at industrial speed is harder than it looks, and the entire line is built around controlling exactly how the mixture changes from hot and fluid to cool and chewy. Granulated sugar and glucose syrup enter the process through automated dosing systems that deliver predetermined quantities into stainless steel dissolving vessels. Water is added in a controlled stream while agitators rotate continuously, pulling dry sugar away from the walls and circulating it through the increasingly clear liquid. Steam inside the vessel jackets provides the heat. Sugar crystals gradually disappear until the contents become a homogeneous syrup that can be pumped without carrying undissolved particles farther into production. Filtration equipment then removes unwanted solids before the syrup reaches the main cooking system. From this point onward, moisture becomes one of the most important variables on the entire line. The syrup enters continuous cookers, where temperature rises and water begins evaporating rapidly. Instead of simply boiling the mixture for a fixed period, the equipment controls the relationship between heat, residence time, and final solids concentration. As water escapes, the syrup thickens substantially. Pumps designed for viscous materials keep it moving, while instruments continuously monitor temperature and flow. The objective is not to make a hard candy syrup. Starburst needs a softer, elastic structure, so the cooking stage stops at a carefully selected condition that leaves enough moisture for chewiness while producing enough body to hold a precise shape later. The next ingredients completely change how that cooked sugar system behaves. Fats and emulsifying ingredients are introduced through separate metering lines, followed by additional components used to build the soft confectionery texture. High shear mixing equipment disperses the fat throughout the concentrated syrup instead of allowing separate oily regions to form. The appearance changes as the mixture becomes more opaque and creamy. This internal structure is critical. The finished candy must deform when bitten and then resist enough to create its characteristic chew rather than shattering like brittle sugar glass. Flavor and color are introduced much later than the basic sugar ingredients because prolonged exposure to high cooking temperatures can change delicate flavor compounds. Concentrated fruit flavor is therefore metered into the warm candy after much of the major heating has already taken place. Strawberry, orange, lemon, cherry, and other formulations are handled as separate production runs or streams depending on the line configuration. Color follows through precisely controlled dosing equipment. Powerful inline mixers disperse both throughout the candy until the entire stream carries an even shade from edge to edge. The mass moving through the pipes may now have the recognizable color of a Starburst flavor, but its final texture still has not been locked in. Acid ingredients provide another crucial part of the flavor profile. Carefully prepared solutions or dry systems introduce controlled acidity into the confection, producing the sharp fruit character that balances the heavy sweetness of the sugar base. Their addition must be carefully timed and thoroughly distributed. Inline mixing elements repeatedly divide and recombine the moving stream, preventing localized concentrations while keeping the process continuous. The candy emerging from this section contains the main components of the finished center, but it remains far too warm and fluid for the square shape waiting later. The hot confection now encounters a very different kind of machinery. Instead of more cooking vessels, it reaches cooling equipment designed to remove heat while continuously moving the product. The candy spreads into a broad layer over chilled surfaces or passes through temperature-controlled rollers that draw heat outward. Its behavior changes almost visibly. A material that flowed under its own weight begins resisting deformation. The surface becomes firmer, while the interior remains warm and pliable. This transition has to happen evenly because the forming equipment ahead needs the candy within a narrow temperature range. Too warm and it smears. too cool and it can resist shaping or fracture. Rather than immediately chopping the cooling mass into pieces, the line first creates geometric consistency. Heavy rollers receive the candy and progressively reduce it to a controlled thickness. Each roller pair applies only part of the total reduction, preventing the material from being compressed too aggressively in a single pass. Edge guides keep the moving slab centered, while thickness gauges monitor the product continuously. Tiny corrections to roller spacing can be made as production continues. The once irregular candy mass becomes an uninterrupted sheet with parallel surfaces and remarkably consistent dimensions. Then the sheet changes direction mechanically. Longitudinal cutting wheels divide the broad slab into narrower strips running continuously along the conveyor. Guide channels separate those strips so they cannot reconnect while the candy is still slightly tacky. The strips pass through additional sizing equipment that refines their width and height until the cross-section closely matches the dimensions needed for an individual starburst piece. Now the line contains multiple endless fruit-colored candy lanes traveling side by side, and the machine waiting ahead will turn those continuous lanes into thousands of separate squares. A synchronized cross-cutting system tracks the exact speed of the moving candy. Blades descend at programmed intervals, cutting across every lane and releasing rows of individual pieces without forcing the conveyor to stop. Timing is crucial because a tiny mismatch between cutting frequency and belt speed would gradually change piece length. Servo motors electronically link the cutter to the conveyor, maintaining nearly identical dimensions even as production speed changes. Each stroke produces another row of squares. Within seconds, the continuous ribbons have disappeared into a moving field of individual starburst centers. Freshly cut candy is still slightly warm, so the pieces are separated and transferred into a conditioning section before wrapping. Controlled air moves around them while the temperature continues falling toward the range needed for high-speed handling. During this period, the surface becomes less tacky and the internal structure stabilizes. The pieces remain soft enough to produce the intended chew, but they become firm enough to survive guides, belts, and wrapping jaws without being squeezed out of shape. This quiet transition is what allows the next machine to move at speeds that would destroy candy arriving directly from the cooker. While the centers condition, huge rolls of printed individual wrapper material are being mounted onto separate unwinding systems. Strawberry, orange, lemon, and other flavor wrappers carry their own colors and graphics, so the correct film must remain synchronized with the candy stream being produced. Tension control rollers pull the material from the reel without stretching it, while registration sensors read printed marks and tell the machine exactly where each design begins and ends. The wrapper is traveling continuously before the first piece even reaches it. Individual starburst pieces enter the wrapping machine in evenly spaced rows. Timing screws, belts, or star wheels separate them so each candy occupies its own position. A measured section of wrapper material meets the piece, folds around the square, and closes tightly around the sides. Depending on the packaging configuration, folding and twisting mechanisms finish the ends at extremely high speed. The movements happen so quickly that the individual steps blur together. Feed, position, fold, close, release. A continuous stream of bare candy enters one side while fully wrapped pieces pour from the other. Now comes a challenge unique to assorted packs. Producing each flavor accurately is only half the process. Separate wrapped streams eventually have to become one controlled mixture. Conveyors carry the individual flavors from their wrapping lines toward accumulation hoppers or blending equipment. Computer-controlled gates release programmed quantities from each stream, preventing one flavor from overwhelming the assortment. Gentle tumbling or merging conveyors redistribute the pieces without crushing their wrappers. Red, orange, yellow, and pink packages mix together until the stream resembles the assortment that will eventually appear inside the finished bag. Before retail packaging, the wrapped candies pass through additional verification systems. Cameras inspect wrapper presence and position, while detection equipment monitors the moving stream for unwanted material. Irregular pieces can be diverted before they reach the weighing machines. The accepted candies then climb on bucket elevators toward multi-head combination weighers mounted above the final packaging line. These weighers solve a problem that simple volumetric filling cannot. Wrapped starburst pieces do not always settle identically, so the machine divides them among many individual weigh buckets. Each bucket records its own weight. A computer evaluates numerous possible combinations in fractions of a second and selects the group whose total most closely matches the target package weight. The chosen doors open simultaneously, sending one accurately measured portion downward while the other buckets continue filling for the next calculation. The cycle repeats again and again without stopping the candy stream. Below the weighing system, a completely separate transformation is happening to the retail packaging film. A large printed roll unwinds through guide rollers and enters a forming collar that bends the flat material around a vertical filling tube. The overlapping edges are sealed into a continuous sleeve. Horizontal jaws close beneath the tube to create the bottom of a new package, and the measured assortment drops inside. Once the candy clears the sealing area, the jaws close again above it, forming the top seam while simultaneously creating the bottom seam for the package that follows. A cutter separates the finished bag, and the process repeats almost instantly. Louisville Slugger baseball bats begin spinning at astonishing speed inside computer-controlled lathes as rough wooden billets blur into smooth cylinders with every pass of the cutting tools. Thin ribbons of maple or ash peel away continuously, collecting beneath the machines, while the bat's familiar profile slowly emerges from what only moments earlier looked like an ordinary block of timber. Even now, however, the bat is still far from complete. The balanced barrel, the precisely tapered handle, and the reinforced striking surface all depend on dozens of tightly controlled manufacturing stages that started long before the first billet ever reached a cutting machine. The process begins deep inside lumber yards, where carefully selected hardwood logs arrive after harvesting. For premium wooden bats, maple, ash, or birch are the most common choices because each species offers a unique balance of density, flexibility, and impact resistance. Massive scanning systems evaluate every log before processing begins, measuring diameter, straightness, and internal consistency. Advanced imaging equipment helps identify defects hidden beneath the bark, allowing sections with knots, irregular grain, or structural imperfections to be removed before they ever reach production. Only the cleanest portions continue toward the sawmill, where the first major transformation takes place. Gigantic bandsaws divide each log into long rectangular planks, while automated conveyors carry every board through additional optimization scanners. These systems examine grain orientation with remarkable precision because the direction of the wood fibers has an enormous influence on how the finished bat behaves under repeated impacts. Computer-controlled cutting equipment then divides the selected boards into shorter rectangular blocks known as billets. Each billet already contains enough material for one future baseball bat, although at this stage it still resembles nothing more than a smooth wooden beam with sharp square edges. Freshly cut billets cannot move directly toward shaping. Wood naturally contains moisture that varies throughout the log, and if left untreated, it could cause the finished bat to warp, shrink, or change weight over time. Instead, the billets enter enormous drying kilns, where carefully controlled heat, airflow, and humidity slowly reduce moisture content over several days or even weeks, depending on the species. Large circulation fans move conditioned air continuously through tightly stacked rows of timber, while computerized control systems constantly adjust temperature and humidity. The drying process happens gradually because removing moisture too quickly could introduce internal stresses or surface cracks long before the bat ever reaches the field. Once drying is complete, every billet returns to another inspection stage. Moisture meters verify internal water content, while scanners once again evaluate grain quality. Workers and automated systems both examine the wood, rejecting any billet showing hidden splits, discoloration, or fiber irregularities revealed during drying. The remaining billets continue toward precision weighing stations, where every piece is categorized according to density. This sorting stage allows manufacturers to match specific wood characteristics with different bat models, ensuring the finished product reaches its intended balance and swing weight. Now the rectangular billets finally approach the lathes introduced at the beginning of the journey. Robotic loading systems position every billet securely between rotating centers before powerful electric motors accelerate the wood to high rotational speed. Computer-guided cutting heads begin removing material in carefully programmed passes. Rather than carving the final shape immediately, the machines gradually reduce the billet through multiple stages. Each pass removes only a thin layer, allowing remarkable dimensional accuracy while preserving a smooth surface. Slowly, the square timber transforms into a perfectly cylindrical blank before the recognizable taper of the bat begins appearing. As the cutting tools continue moving along the spinning wood, the thick barrel develops first. Further down the blank, the profile narrows steadily into the handle before widening slightly again at the knob. Every contour follows digital specifications accurate to fractions of a millimeter. Laser measuring systems positioned beside the lathes monitor dimensions continuously, while automatic corrections compensate for even tiny variations in cutting tool wear. What appears to be a simple wooden club is actually the product of highly controlled machining, where balance, weight distribution, and geometry are engineered with extraordinary precision. The freshly turned bat still carries fine machining marks left by the cutting tools, so it immediately enters sanding stations designed to refine every surface. Wide abrasive belts and rotating sanding heads glide smoothly across the spinning wood, removing microscopic imperfections without altering the carefully machined profile. The sanding sequence progresses through increasingly finer abrasives until the entire bat develops an exceptionally smooth finish. Fine wood dust is extracted continuously through high-powered vacuum systems, keeping the cutting surfaces clean while preventing dust from settling back onto the product. Although the bat already feels smooth, another critical process now begins. Branding and identification markings are applied through laser engraving or precision stamping systems depending on the production method. Logos, model numbers, wood species, and manufacturing information are positioned accurately along the barrel before permanent markings are burned or pressed into the surface. This stage also establishes the preferred hitting orientation for many wooden bats by identifying the optimal grain alignment. Those markings later help players strike the ball using the stronger side of the bat's grain structure. Before any finish is applied, every bat undergoes another detailed inspection. Operators rotate the bat beneath bright lighting, while optical systems examine the grain from end to end. Straight, uninterrupted grain lines are especially important for premium models because they contribute significantly to impact performance and durability. Even minor surface defects that escaped earlier inspections become much easier to detect after machining and sanding. Only bats meeting strict visual and dimensional standards continue toward finishing. Now the wood begins receiving the protective coatings that give many baseball bats their rich appearance. Depending on the model, automated spray systems apply stains ranging from natural clear finishes to deep black, rich brown, cherry, or other colors. Each coating settles evenly across the sanded surface, while the bats rotate slowly to eliminate runs or uneven coverage. After staining, the bats enter drying tunnels where carefully controlled airflow allows solvents to evaporate gradually without disturbing the finish. The grain pattern becomes dramatically more visible beneath the transparent coatings, revealing the natural character hidden inside the wood. Once the stain has cured, clear protective top coats are applied through another series of automated spray booths. Multiple thin layers build gradually instead of relying on one heavy application. Each coat protects the wood from moisture while producing the smooth finish associated with professional quality bats. Between coats, the bats travel through curing tunnels where temperature and airflow remain tightly controlled. Every additional layer increases durability while preserving the natural balance engineered during machining. Some models receive additional surface polishing after the final clear coat cures. Soft polishing wheels rotate gently against the barrel and handle, producing a consistent satin or gloss appearance depending on the intended finish. The polishing stage removes tiny dust particles or surface irregularities that may have settled during curing while creating an exceptionally smooth feel in the player's hands. Weight and balance testing now become the primary focus. Every finished bat passes across highly accurate electronic scales that verify total weight before specialized balancing equipment measures the distribution of mass along its length. Even two bats sharing identical dimensions can feel very different if weight distribution changes slightly. Manufacturers therefore compare each bat against strict balance specifications, ensuring the finished product delivers the swing characteristics expected for that model. Tropicana orange juice begins changing long before it ever reaches a bottle, because the most valuable part of the fruit is separated only seconds after the peel is broken. Fresh oranges arrive at the processing facility in enormous loads before moving onto wide receiving conveyors that feed the first stage of production. Leaves, small branches, and loose debris are removed immediately as the fruit passes beneath air blowers and oversorting equipment. From there, thousands of oranges travel through long washing channels where powerful sprays and rotating brushes scrub every piece of fruit from multiple directions. Dirt, dust, wax residues, and anything collected during harvesting are washed away while the oranges tumble gently across the rollers. By the time they leave the washing line, every orange has a clean surface, but the real transformation has not even started. Everything so far has simply prepared the fruit for the moment when machines finally reach the juice hidden inside. The cleaned oranges continue across inspection conveyors where cameras and optical sensors examine their size, color, and external condition. Mechanical diverters remove fruit that falls outside programmed limits, while the accepted oranges continue forward in an uninterrupted stream. At first glance, the line appears calm, but every conveyor is carefully synchronized because the extraction machines ahead work at remarkable speed. Hundreds of oranges every minute approach the point where peel, juice, pulp, and seeds will all separate into completely different production paths. Each orange enters an individual cup inside the extraction machine. Matching cups close around the fruit, holding it firmly without crushing it prematurely. A stainless steel tube pushes downward through the center, while pressure squeezes the orange between the supporting cups. Instead of simply cutting the fruit open, the system presses juice from the inside while keeping much of the bitter peel oils separated from the liquid. Juice, pulp, and fine fruit particles rush downward into collection channels, while peel sections follow an entirely different route. The extraction lasts only moments, yet in that brief instant, the whole orange becomes several individual material streams, each destined for a different purpose. The freshly extracted juice immediately passes through coarse screening systems designed to remove seeds, larger membrane fragments, and oversized pulp pieces. Stainless steel screens allow liquid and fine pulp to continue while larger solids remain behind. Pumps transfer the screen juice into enclosed pipelines before oxygen has much opportunity to affect freshness. The liquid still contains natural pulp, microscopic fruit particles, and dissolved fruit components that give orange juice its body and appearance. Meanwhile, the peel begins its own journey. Although no longer needed for bottled juice, the peel still contains valuable compounds. Mechanical presses recover peel oils from the outer rind before the remaining material moves toward other processing operations. Nothing about the orange simply disappears once extraction is complete. Every section of the fruit enters equipment specifically designed for that material. Back in the juice stream, another important separation takes place. Centrifugal equipment spins the liquid at high speed, allowing heavier pulp particles to separate from the thinner juice. Depending on the intended product style, processors can remove part of the pulp, retain all of it, or later blend controlled amounts back into the finished beverage. This flexibility allows one production line to create products ranging from pulp-free juice to varieties containing generous amounts of natural pulp. At this stage, the liquid finally resembles recognizable orange juice, yet several important transformations still remain. The juice moves toward deaeration equipment where dissolved oxygen is carefully reduced. Oxygen naturally enters during extraction as fruit breaks apart, but too much oxygen can gradually affect flavor quality over time. Inside enclosed vessels operating under controlled conditions, unwanted gases separate from the juice before it continues deeper into the factory. Now the process begins preparing the juice for long-term stability. The juice enters pasteurization through enclosed stainless steel pipelines connected to large plate heat exchangers. Heat transfers rapidly across thin metal plates, while carefully controlled temperatures raise the juice just enough to reduce unwanted microorganisms without unnecessary damage to flavor or color. The heating stage lasts only a short time before another section of the exchanger immediately begins cooling the juice again. This rapid transition preserves much of the fresh fruit character while creating a product suitable for refrigerated distribution. Although pasteurization appears simple from the outside, it represents one of the most carefully controlled stages in the entire factory. Temperature sensors monitor the liquid continuously, while automated valves ensure every portion receives the required treatment. If any section falls outside specification, control systems immediately divert it away from finished production until correct conditions return. The cooled juice now enters insulated storage tanks that rise several stories high. Slow-moving agitators keep the contents uniform without introducing unnecessary air. These tanks serve as temporary reservoirs between juice preparation and packaging, allowing downstream filling lines to operate continuously even while upstream extraction rates fluctuate. Level sensors constantly monitor every tank, automatically directing juice wherever production requires it. Some production schedules require blending before filling begins. Juice from different storage tanks may combine to achieve the desired balance of sweetness, acidity, aroma, and pulp level. Automated flow meters control each incoming stream, while mixing systems gently circulate the combined juice until every section of the tank matches the next. Even though the beverage comes directly from fruit, consistency across thousands of bottles depends on these carefully controlled blending operations. While juice waits inside storage, packaging materials begin their own journey through the factory. Plastic bottles often start as compact PET preforms that look nothing like finished beverage containers. These thick plastic tubes already contain the bottleneck and threaded opening, but lack the familiar body shape. Preforms travel into heating ovens where infrared lamps soften only the body section while leaving the neck rigid. Each preform rotates continuously to achieve even heating before moving toward the blow molding machine. Inside the blow molder, molds close tightly around each heated preform. A stretch rod pulls downward through the softened plastic, while high-pressure compressed air expands it outward against the chilled mold walls. Within seconds, every contour appears: the base, shoulder, sidewall, grip panels, and label area. The newly formed bottle exits, lightweight yet strong enough to survive filling, transport, and handling. Before filling, every bottle passes through internal cleaning. Bottles invert, while filtered air or treated rinse water removes any particles that may have entered during handling. They drain immediately before returning upright and moving toward the filling system. Cartons follow an entirely different preparation path. Flat laminated carton material unwinds from large rolls before folding into rectangular tubes. Longitudinal seams seal continuously while sterile systems prepare the interior for juice filling. Every packaging format follows its own engineering approach, but each shares the same objective: protect the juice from contamination while preserving quality during storage. Fanta turns bright orange inside a sealed stainless steel blending tank as a concentrated flavor base is pulled into a fast-moving stream of treated water and sweetener, creating thousands of liters of soft drink before a single bubble has been added. Powerful agitators circulate the liquid from the bottom of the vessel to the top, eliminating streaks of concentrate until the entire batch reaches one uniform color. It already looks remarkably close to finished Fanta, but it is still completely flat. The characteristic fizz will only appear after the liquid has been chilled, pressurized, and exposed to precisely metered carbon dioxide, and that transformation cannot happen until the factory has built an exceptionally consistent beverage base. The water entering the blending system has already passed through its own extensive preparation line. Incoming water moves through filtration equipment designed to remove suspended particles before continuing through additional treatment stages selected for the chemistry of the local supply. Activated carbon systems can remove compounds that might interfere with flavor, while fine filtration provides another physical barrier before the water reaches storage vessels. Where required, mineral composition is adjusted so the water entering the beverage process remains consistent from batch to batch. Pumps maintain continuous flow through enclosed stainless steel pipelines, and instruments measure properties such as conductivity, pressure, and temperature as the treated water moves toward production. That consistency matters because water forms the overwhelming majority of the finished drink. Even a small variation could become noticeable after flavor, sweetener, acid, and carbonation are added. The treated water therefore enters sanitary holding tanks, where it remains isolated from the raw incoming supply. From here, automated valves release exact quantities toward the syrup room, according to the production schedule. The next stage looks simple from the outside, but inside the tanks, one of the densest ingredients in the entire process is being prepared. For sugar-sweetened formulations, granulated sugar is transferred from bulk storage into dissolving vessels containing measured quantities of heated treated water. Heavy-duty agitators begin rotating as sugar enters, pulling the crystals downward and preventing them from accumulating on the vessel floor. The cloudy mixture becomes increasingly transparent as the crystals disappear into solution. Temperature remains carefully controlled to accelerate dissolution without exposing the syrup to unnecessary heat. Once the target concentration is reached, the resulting simple syrup is pumped through filtration equipment before entering a dedicated holding tank. Other Fanta formulations may use different sweetening systems, but the same principle remains. The sweetener has to be measured and dispersed so precisely that every liter reaching the filler tastes the same. The clear sweetener base is still missing almost everything that makes the drink recognizable. In separate preparation vessels, concentrated flavor components are readied for addition. Depending on the Fanta variety and regional formulation, these systems can contain citrus flavor preparations, fruit-derived components, acids, color ingredients, stabilizing ingredients, and other precisely measured beverage components. Each material is dosed through its own controlled system because some ingredients are required in quantities dramatically smaller than the water or sweetener. Metering pumps can therefore deliver relatively tiny volumes into enormous batches while maintaining consistent proportions. The flavor concentrate meets the sweetener and treated water inside large blending tanks. Agitators immediately begin circulating the combined liquid, while automated dosing systems introduce the remaining components in a programmed sequence. Acids adjust the characteristic sharpness and overall flavor balance. Color ingredients create the familiar appearance of the selected variety. Flavor preparations disperse throughout the mixture, and stabilizing systems help maintain uniform distribution where the formulation requires them. The order of addition is controlled carefully because concentrated ingredients can behave differently if they encounter one another before being diluted. The mixture now circulates through the tank until sensors and production controls confirm that blending is complete. Samples or inline instruments can be used to verify parameters such as soluble solids, concentration, and acidity before the beverage base is released. At this moment, the factory has produced something that tastes much closer to Fanta, yet pouring it into a glass would reveal one obvious difference. There is almost no carbonation. Creating those millions of bubbles requires a sudden change in both temperature and pressure, and the beverage is about to enter equipment built specifically for that purpose. First, the blended liquid moves through heat exchangers that rapidly lower its temperature. Chilling is important because carbon dioxide dissolves much more effectively in cold liquid than warm liquid. Instead of placing an entire tank inside a refrigerator, the factory pumps the beverage through narrow stainless steel passages separated from a colder fluid by thin metal surfaces. Heat transfers rapidly through the metal while the two liquids remain completely separate. The Fanta base emerges significantly colder within seconds, ready for pressurized carbonation. The chilled beverage enters a carbonator where carbon dioxide is introduced under carefully controlled pressure. Gas disperses into the moving liquid through specialized contact systems designed to maximize interaction between the two phases. Under elevated pressure, carbon dioxide dissolves rather than immediately escaping as bubbles. Flow meters and pressure controls continuously regulate the gas to liquid ratio, allowing the line to maintain a consistent carbonation level even while thousands of liters pass through every hour. The bright beverage now contains the familiar fizz, although much of that gas remains invisible as long as the liquid stays cold and pressurized. From this moment forward, the production line has to preserve that dissolved carbon dioxide. Sudden pressure drops or excessive turbulence could release gas prematurely, filling pipelines with foam and making accurate filling difficult. The carbonated Fanta, therefore, travels through enclosed pressure-rated pipes directly toward the filling equipment. But while the drink has been taking shape, another production stream has been preparing the containers that will receive it. On PET bottle lines, production can begin with compact plastic preforms that resemble thick test tubes with finished bottle necks already molded into them. These preforms enter heating ovens where infrared elements warm the plastic body while leaving the threaded neck dimensionally stable. The softened preforms transfer immediately into blow molding machines. Each one enters a bottle-shaped mold. A stretching rod extends downward, and high-pressure air expands the hot plastic outward until it contacts every detail of the chilled mold wall. In seconds, a small preform becomes a full-size Fanta bottle. Freshly formed bottles leave the molds at high speed and move directly into an enclosed air conveyor system. Rather than standing entirely on conventional belts, lightweight empty bottles can be guided by their neck rings while streams of filtered air push them forward. They race around curves and merge into single-file lanes leading toward the filler. Their thin walls make them extremely light when empty, but that changes almost immediately once hundreds of grams of carbonated beverage enter each container. Dr. Pepper comes to life the instant a stream of invisible carbon dioxide disappears into an ice-cold beverage, because everything that happens afterward depends on keeping that gas trapped until the very second the bottle or can is opened. The carbonator sits at the center of the production line, receiving a chilled, completely flat drink from the blending system. At this stage, the beverage already has its sweetness, acidity, color, and signature flavor profile, but it has no sparkle. Inside the sealed vessel, carbon dioxide enters under carefully controlled pressure. Instead of forming large bubbles, the gas breaks into microscopic pockets that dissolve into the liquid. Within moments, the beverage becomes fully carbonated, transforming from a still drink into Dr. Pepper. That invisible transformation only works because of everything that happened before it. Long before carbonation begins, treated water enters the factory through stainless steel pipelines. Water makes up the majority of the finished beverage, so every batch starts here. The incoming supply passes through multiple treatment stages designed to create a consistent foundation. Fine filtration removes suspended particles. Activated carbon beds reduce unwanted taste and odor compounds. Additional polishing systems stabilize the water before it reaches large storage tanks. The treated water leaves storage only when the blending system calls for it. Pumps move the clear liquid toward the syrup preparation area, where another process has already been underway. Inside a separate mixing vessel, sweetener forms the backbone of the syrup. If granulated sugar is used, controlled feeders deliver measured quantities into circulating treated water. Powerful agitators keep the liquid moving while the sugar dissolves. At first, individual crystals swirl through the tank. Gradually, they disappear until the liquid becomes completely uniform. If liquid sweetener is used instead, it enters through heated stainless steel lines. Flow meters continuously monitor the addition, ensuring every batch matches the previous one. Regardless of the sweetener source, the objective remains identical. Produce a perfectly uniform sweet base with no undissolved solids. The sweet base travels through filtration before anything else is added. Even tiny particles could interfere with precision flow meters, pumps, or filling equipment later in the process. Once filtered, the syrup moves toward the blending vessel, where the drink begins developing its recognizable identity. Now comes one of the smallest additions in volume, but one of the biggest changes in character. The concentrated Dr. Pepper flavor system enters through enclosed dosing lines. Only a carefully measured amount is needed because it is highly concentrated. As it enters the circulating syrup, darker ribbons briefly appear before disappearing into the moving liquid. The entire tank gradually changes into a deep brown concentrate that now contains sweetness, acidity, color, and the complex flavor profile that defines the beverage. Despite its appearance, this still is not Dr. Pepper as consumers know it. The syrup is far too concentrated to drink. It exists only as a compact version of the final beverage. After blending, the syrup enters insulated holding tanks equipped with slow-moving agitators. These paddles rotate gently, preventing heavier ingredients from settling while avoiding unnecessary air incorporation. Level sensors monitor the remaining volume continuously, so the production line always has enough concentrate available. Soon, the syrup begins its journey toward the proportioning system. Meanwhile, treated water follows a completely separate route toward the same destination. Two independent streams, one clear, one dark, approach the blending skid from opposite directions. Electronic flow meters measure both streams thousands of times every hour. Computer-controlled valves constantly make tiny adjustments. If production speeds increase, both streams accelerate together. If demand slows, they reduce proportionally. Maintaining the precise syrup-to-water ratio is essential because every bottle leaving the line must taste identical. Inside the proportioner, the concentrated syrup merges with treated water. Almost instantly, the dense concentrate disperses throughout the much larger water stream. the beverage now reaches its final drinking strength. It still lacks one defining feature. The beverage leaves the proportioner completely flat. Before carbonation can begin, temperature must change dramatically. The freshly blended drink enters a plate heat exchanger where thin stainless steel plates separate the beverage from a chilled cooling medium. Heat transfers rapidly through the metal surfaces. Within seconds, the beverage temperature drops substantially. This colder temperature prepares the liquid for something impossible at warmer conditions. Carbon dioxide dissolves far more effectively in cold liquid. Before the gas enters, another hidden process often takes place. The beverage passes through a deaeration stage where dissolved oxygen and unwanted air are removed. Tiny gas pockets separate from the liquid under carefully controlled conditions. Removing these gases improves carbonation efficiency and helps maintain long-term product stability. Only after chilling and deaeration does the beverage finally reach the carbonator. Inside the sealed vessel, carbon dioxide enters through specialized diffusers. Pressure builds while the beverage continues flowing. Rather than forming visible fizz, the gas dissolves directly into the cold liquid. The beverage still appears calm, but its internal chemistry has completely changed. From this moment forward, every machine on the line has one mission: never allow that dissolved gas to escape. The carbonated Dr. Pepper flows through sealed stainless steel pipelines maintained under pressure. Sharp turns are minimized. Sudden pressure drops are avoided. Smooth piping reduces unnecessary turbulence. While the beverage travels toward filling, empty containers begin an entirely different journey. PET bottles often begin as small plastic preforms. These thick test tube-shaped pieces already contain the finished bottle neck and threaded opening. Their bodies, however, remain compact. Preforms enter a heating oven where rows of infrared lamps warm only the body section while the neck stays cool. Every preform rotates continuously, ensuring even heating around the circumference. Once softened, each preform moves into a blow mold. The mold closes instantly. A stretch rod pulls downward through the center, while high-pressure compressed air expands the softened plastic outward. The material stretches until it contacts every detail inside the chilled mold cavity. Base, shoulders, sidewalls, and label panels all appear within seconds. The finished bottle exits remarkably lightweight, yet surprisingly strong. Air conveyors transport empty bottles by supporting only their neck rings. Jets of filtered air propel them rapidly through the system while preventing contact with sidewalls. Before filling, each bottle passes through an internal rinsing station. Bottles invert, receive filtered air or treated rinse water, drain immediately, then rotate upright again. Aluminum cans follow a different route. Already formed and decorated, empty cans arrive stacked on pallets. Depalletizers unload entire layers before guiding individual cans into high-speed conveyors. Each can inverts through an air or water rinser to remove any loose particles. After draining, the cans continue upright toward the filling carousel. Now both product streams finally meet. Inside the rotary filler, containers travel in perfect synchronization beneath filling valves. For bottles, each neck seals tightly against its valve before filling begins. Pressure inside the bottle equalizes with pressure inside the filler bowl. Without this equalization, dissolved carbon dioxide would immediately burst out of solution, creating excessive foam. Once pressures match, the valve opens. Dr. Pepper flows smoothly into the bottle. The dark liquid rises rapidly, while only a controlled amount of foam develops near the surface. Electronic controls determine the exact fill level before the valve closes. Each filled bottle immediately transfers toward the capping turret. Caps travel through sorting bowls that orient every closure correctly before delivery to spinning capping heads. Each head applies precisely controlled torque. Tight enough to seal carbonation, not tight enough to damage threads. Aluminum cans move directly into the seamer. Lids drop onto each filled can moments before rotating beneath seaming rollers. The first roller folds the lid curl around the can flange. The second roller compresses both layers into a tightly interlocked double seam. No glue is used, only precisely folded metal holds the internal pressure. Now another important checkpoint arrives. Sophisticated inspection systems immediately verify every package. Vision cameras examine fill height, cap alignment, tamper bands, seam profiles, dents, scratches, and container deformation. Then you think marbles emerge from the polishing drums with a deep glassy shine, rolling across vibrating conveyors like hundreds of tiny mirrors catching the factory lights from every direction. At first glance, they appear completely finished, but one final inspection still waits ahead, and it is surprisingly unforgiving. A single air bubble trapped too close to the surface, a swirl that drifted slightly off center, or a diameter that varies by less than a fraction of a millimeter can remove an otherwise perfect marble from the production line. That level of precision begins long before the polishing stage, because every marble starts as nothing more than carefully measured raw minerals that must first become perfectly molten glass. The process begins with massive storage silos holding the ingredients that will eventually become crystal clear glass. Fine silica sand forms the largest portion of the mixture, providing the silicon dioxide needed for the finished product. Soda ash lowers the temperature required to melt the sand, making continuous production far more practical, while limestone strengthens the finished glass and improves its long-term durability. Depending on the style of marble being produced, additional minerals and carefully prepared colorants are stored in separate hoppers waiting for later stages. Every ingredient passes through automated weighing systems, capable of measuring enormous quantities with exceptional accuracy before traveling toward industrial mixers. Inside the blending equipment, wide ribbon paddles continuously fold the dry ingredients together until the entire batch becomes completely uniform. The powders flow almost like liquid as they tumble from one end of the mixer to the other, leaving no visible separation between sand, soda ash, limestone, or the smaller mineral additions. Consistency at this stage is essential because even slight variations would become far more noticeable once the mixture enters the furnace. When computerized controls confirm the correct composition, enclosed conveyor systems transport the blended material toward one of the hottest environments anywhere inside the factory. Towering glass furnaces operate continuously, often for years without shutting down. The blended raw materials enter gradually through automated charging systems, disappearing into an intense chamber where temperatures rise well above 1,400 degrees Celsius. At first, the ingredients remain recognizable as individual particles, but within minutes, the heat begins breaking apart their original structure. The sand softens, soda ash reacts with silica, limestone decomposes, and everything gradually combines into one glowing liquid mass. Powerful burners maintain remarkably stable temperatures throughout the furnace, while the molten glass moves slowly through carefully designed channels. Hidden beneath the brilliant orange glow, thousands of tiny chemical reactions continue eliminating the boundaries between the original ingredients until only perfectly molten glass remains. Even after the mixture has melted completely, it still cannot move directly toward marble production. Tiny gas bubbles generated during melting remain suspended throughout the liquid glass. And if left untouched, they would become visible imperfections inside the finished product. To solve this, the molten glass spends additional time inside refining zones, where carefully controlled temperatures allow trapped gases to rise naturally toward the surface. The glowing liquid appears calm from above, yet microscopic bubbles are continuously escaping while the glass becomes increasingly clear. This refining stage quietly determines the optical quality that will later allow light to travel cleanly through every marble. Once refining has been completed, the molten glass begins flowing through insulated forehearth channels leading away from the furnace. These channels do much more than transport the material. They gradually reduce its temperature until the viscosity reaches exactly the level required for forming. Glass that remains too hot flows uncontrollably, while glass that cools too much becomes too stiff to shape consistently. Temperature sensors positioned throughout the forehearth constantly communicate with automated controls that adjust heating elements in real time, ensuring every section of glass reaches the forming equipment under nearly identical conditions. Now another stream of molten glass joins the process. Separate furnaces or color feeders prepare vividly colored glass using carefully measured metal oxides and mineral pigments. Cobalt compounds produce brilliant blues. Chromium creates greens. Selenium and cadmium formulations generate reds and oranges, while countless other combinations create the rich palette used inside decorative marbles. These colored streams remain completely molten as they travel toward the clear glass flow, setting the stage for one of the most visually fascinating moments in the factory. Instead of mixing the colors completely into the clear glass, precision feeding systems inject narrow streams of colored, molten glass directly into the larger flow. The different colors stretch and fold naturally as both materials continue moving together without fully blending. Depending on the arrangement of the feeders, the glass develops ribbons, spirals, flames, cat's eye patterns, or intricate swirls running through its interior. Every movement inside the flowing stream influences the final appearance. Tiny adjustments to feeder position or flow rate can dramatically alter the patterns trapped forever inside each marble. Although the glass still resembles one continuous glowing ribbon, countless unique designs are already beginning to form. The patterned molten glass now reaches the marble forming machine. Instead of pouring into individual molds, the glass exits through carefully engineered openings as continuous cylindrical streams. Rotating cutting mechanisms positioned beneath the outlets divide the flowing glass into precisely measured gobs, each containing just enough material to produce one finished marble. Timing here is extraordinary. Every cut must occur while the glass remains soft enough to shape but consistent enough to maintain identical volume from piece to piece. As each glowing gob separates, gravity carries it immediately toward the next transformation. The freshly cut glass pieces fall onto rapidly rotating grooved rollers arranged in matched pairs. This stage almost seems magical. As every glowing gob lands inside the moving grooves, continuous rolling motion begins rounding it automatically. The glass rotates rapidly in every direction, while surface tension naturally encourages it toward a perfect sphere. Unlike machining metal into a ball, the factory relies heavily on the physical properties of molten glass itself. Every rotation smooths tiny irregularities while preserving the intricate, colored patterns already suspended inside. Within only a few seconds, rough glowing pieces become nearly flawless spheres rolling steadily toward the cooling system. Although the marbles now have their final shape, they remain far too hot to handle. If allowed to cool too quickly, enormous internal stresses would develop throughout the glass, making the marbles surprisingly fragile despite their hard appearance. Instead, every sphere enters a long annealing oven designed specifically to remove those stresses. The marbles travel slowly through zones where temperature decreases almost imperceptibly over an extended period. Inside the annealing layer, the glass gradually relaxes, while internal molecular movement redistributes residual stress evenly throughout every sphere. Nothing dramatic appears to happen while the marbles move through this tunnel, yet this quiet thermal treatment determines whether they will survive impacts for decades or crack unexpectedly after leaving the factory. When the marbles finally emerge from the annealing oven, they have cooled completely to room temperature, while retaining exceptional strength. Conveyor belts transfer them toward cleaning systems, where any remaining traces of furnace residue or handling marks are removed. Soft rotating brushes, filtered water sprays, and carefully controlled drying equipment restore complete clarity to every surface. For transparent marbles, this stage reveals the intricate internal patterns that have been hidden behind slight surface haze since forming. Swirls, ribbons, flames, and colored cores suddenly appear with remarkable sharpness. Even now, the manufacturing process is not complete. The cleaned marbles enter large polishing drums lined with carefully selected polishing media. As the drums rotate slowly, thousands of marbles gently roll against both the polishing material and one another. Minute surface imperfections gradually disappear while the glass develops its familiar brilliant luster. The polishing stage removes almost immeasurable amounts of material, yet the visual difference becomes immediately obvious. Light begins, reflecting cleanly across every surface, giving each marble the deep, glossy appearance associated with high-quality glass.